Hello, and welcome to the full course session on Introduction to Physical Modeling using Simscape, your gateway to mastering the simulation and modeling of complex systems through Simulink and Simscape. This is a certified course session, so make sure to fill out the form in the description after completing the session to claim your certificate. You can now proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we're committed to providing industry-relevant advanced engineering courses. We partner with industry experts to offer top-notch training that equips you with the skills needed to excel in your engineering career. Don't forget to subscribe to our channel for more insightful tutorials and updates on Simulink, Simscape, and other engineering tools. Hit the subscribe button and stay tuned. Here's a brief overview of what we'll cover in this training video. In the first chapter, we'll introduce you to the basics of modeling complex systems. You'll learn about the importance of mathematical modeling and how the block diagram approach and model-based design apply to engineering systems. We'll introduce you to the Simulink environment, guide you through creating a simple model, and show you how to obtain results. We'll also give an overview of the various Simulink toolboxes that are available. In the second chapter, we'll dive into simulation configurations in Simscape. You'll learn how a model runs in Simulink, the different types of solvers available, and how to configure models for both continuous and discrete time systems. We'll explain how to solve ordinary differential equations and give you an introduction to physical modeling using Simscape. In the third chapter, we'll cover how to work with Simulink using script files and the workspaces. You'll learn how to create subsystems and variant subsystems, work with lookup tables, and run simulations in steps. We'll also explore templates and projects, enhancing your ability to manage complex models effectively. In the fourth chapter, we'll introduce you to Stateflow for control logic. You'll learn how to implement control logic for engineering applications using finite state machines and how to create logic diagrams, providing a foundation for control system design. Thank you for joining us. We're excited to have you on this learning journey. Make sure to subscribe for more updates and detailed tutorials. Complete the training, earn your certificate, and share your achievement on LinkedIn. Let's get started with Introduction to Physical Modeling using Simscape.
Hello everyone, we all know the importance of Matlab and Simulink in the engineering field. Matlab is used to analyze data, develop algorithms, and to create models. It also provides some sets of applications through which we can learn how algorithm basically deals with data evaluation. Simulink is a tool used for simulation of model-based design. If you're designing a system and before you get it on the ground, you can simulate it using this tool to make it more efficient and error-free. So here we will see how to download the Matlab R2020 trial version. Let's go onto Google and search for MathWorks. MathWorks is the organization which has developed Matlab and Simulink. So now click on the first link that's available here and let's get proceeded. Click on Get Matlab. Scroll down and select Download a trial. Here in this space you can provide your mail ID and click on I agree and then submit it. These are the trial packages available for downloading, out of which we'll select only Simscape Essentials. These are the required products in Simscape. Click on Select and Continue. Here you can view the three options for selecting the type of operating system that you are using. Select one as per your requirement. Suppose I'm using Windows and I click on it, and then this dialog box appears which asks for me to save the file. Click on Save File and wait for the Matlab file to be saved. Once you finish this process, you can activate your Matlab account using the same mail ID and password. After you are done activating, you can open Matlab, and this is how the Matlab window looks like. Click on Simulink to open it. So this is the Simulink window. If you click on Library Browser, you will be able to see the toolboxes that are available in Simulink. So here is the Simscape toolbox. These are the different tools available under Simscape. If you double click on any of this, you can see the different components that it consists of. Hope by now you have got it how to download Matlab and Simulink. All the best, keep going.
Hi everyone, welcome to the course of Simulink for Mechanical Engineers. In this course, you are going to learn about how you can use Simulink for mathematical modeling. This is the part 1 where we are going to learn about introduction to modeling of complex systems. Let's begin with what are course contents and what this course is about. This course will explain you about the importance of the mathematical modeling and why we should learn about it. We are going to have introduction of Simulink environment and how you can begin with the Simulink. How you can start from the first step, how you can open the Simulink, how you construct very fundamental diagrams, and how to run the simulation and how to visualize the results. So this complete simulation process is going to be explained in this course. These models are going to be basic systems of mechanical and electrical systems. So these models will be related to these two engineering disciplines. We are also going to learn about physical system modeling using Simscape. So Simscape is a different block set within the Simulink which is very popular for electromechanical simulation. So Simscape involves both the cases where electrical and mechanical systems are simulated in coexistence, or when electrical and mechanical both the systems are present in the same model. We are also going to learn about Matlab and Simulink interface. So if you have learned basic Matlab programming or script writing and running your program and execution of .m files, you can actually link with your Simulink model, and we will learn about how to connect the script file with a model file. And last, we are also going to learn about how to implement the control logic with the Stateflow. So Stateflow is another important Simulink feature, or I will say a block set, which will help you to realize how the control logic can be implemented. And this can be clubbed with your model and you can learn how the control logic works in a simulated environment. So what are the course objectives? At the end of the course, you will be able to become familiar with Simulink and model-based design. So we are going to discuss what is a model-based design, and this is nothing but a system level, or we can say a higher level design in a simulated environment. You will be able to start making beginner level models. You will be able to configure the model properties correctly, and after you have hit the run button, you will be able to see the results as well, and you will be able to make the post-processing analysis. So how to analyze your result, how you can actually do the further saving of your result data, how you can generate a better report out of it, or maybe if you want to transfer your data points into the Excel sheet, for example, you will be learning that as well. So these are the main course objectives, and let's start with importance of mathematical modeling. Why we need to do mathematical modeling? So if you see this image, there are few civil engineers standing on the bridge and they are discussing something about what went wrong. So this is a bridge construction happening and this is not in line with the other end, right? So what is going to happen if the engineering projects are not planned and not executed properly? So this is one such example where you will end up making a big mistake, and that will not cause only the time is consumed but also many investments, and it is also going to affect many other parameters, and you may require to have major corrections in the design implementations. So the planning and execution of a technical project are very important parts. So if these two steps are going to not fall in place, if they are going to be incorrect, then the entire project is going to suffer and you will not get final outcome as per your expectations. So realization or implementation or execution must be well planned, right? So for any technical project or any engineering project, the planning is very much essential. Without planning, you cannot actually go to the next step, which is realization or implementation or execution. So if you take up any other project related to electrical engineering, let's say if it is a case of substation design, right? So in case of setting up a substation for electrical power, you need to decide about the location, about the voltage level, about how much power you are going to feed into what lines, and what exactly are the fundamental requirements. So those planning is done, then the next step is going to be the execution. So any technical project, the first phase is very, very important. So what is exactly this planning? What are the parameters, or what exactly are the steps in the planning, right? So let's discuss more about what the meaning of planning is. So planning is actually the estimation and creating a model of the system. So here comes an important term, a model. So what is a model of a system? So model of a system is nothing but the mathematical representation of subsystems as well as main system, and it is expected to behave same as the actual system. So for example, an electrical system model, we can take, let's say there is a transformer in the substation. So this transformer in a substation is going to have some input power and output power. So what this transformer is going to basically do, that can be implemented by a model which is going to represent the behavior of the entire system. We can take up any other simple example related to mechanical engineering. Let's say this block represents a simple gearbox. So whatever is the input speed and torque, the output speed and torque will be divided by some ratio, and that is called a gear ratio. So how do we mathematically represent the gear ratio? So gear ratio can be a simple number, and which you can assign in a block. So the model of a system is nothing but a representation or mathematical equation representation of that particular system of interest. So the next important term which we are going to learn is what is a simulation. Once you have the model ready, right? So once you have let's say made a gearbox model. So a gearbox model in a most simple term can be written like a constant number, which is a gear ratio. Let's say there is a input torque and speed over here. Let's say T torque and the omega speed, which is on the input side, and they are denoted as torque T1 and omega 1. On the output side, or let's say the driven shaft, this is the input side or driving shaft. This is a driven shaft, and on this shaft we have torque T2 available and speed omega 2. And this gear ratio or this block is going to just represent a constant number x in an ideal condition. So now if you have built this model, now you try to create a real life situation. What is a real life situation? Where you decide about some T1 and omega 1 values and you check out what is a T2 and omega 2 value. Well, if it's just a ratio, these values will be either multiplied or divided. But if you want to add some other inputs, let's say it's a variable gear, or you want to also incorporate the amount of losses happening in a gear, or let's say you want to add some non-linearities to the gear, right? So how you can do that? So for that you need to create a detailed mathematical model, right? So what are the real life situations? So for example, a civil engineer created a model of a bridge, right? And this bridge model is to be tested for earthquake situation, right? Let's say this understanding of behavior with the effect of earthquake is going to be called a simulation, right? So when you provide the predefined inputs to a model and you analyze the output, that situation is, or that process is called making out a simulation. So when you were a child, you must have played a car racing game or maybe any other different game. Now actually, what is this game? Now this game is a virtual environment where you believe that you are inside a car and you are driving and you are visualizing the road conditions and visualizing the other cars and other systems which are coming up in the road environment. So actually the programmer who created this game has made a model of running a car in a typical situation. So a car racing game is nothing but a model given to you to play with, right? So now you can have the direction related inputs, the acceleration and braking related inputs, and many other configurations. So effectively, a car racing game is nothing but a mathematical model given to you to play with, to run a simulation of. So while you are playing a car racing game, you are actually doing a simulation. So a simulation is nothing but a virtual environment. So virtual environment represents how virtually the things will happen. So simulation is not reality, but it is a fictitious arrangement or fictitious setup of a system where you make the use of a mathematical model and try to understand how it behaves, right? So another important term after the model is a simulation. So simulation is a virtual environment where you run your model, right? So what is the meaning of running your model is execute, right? So you provide some inputs to the model and you focus on what are the outputs, in this example T2 and omega 2. So when you run your model, it is going to be created as a fictitious situation, right? So if I give you better idea about, let's say, how exactly a simulation will look like, right? A better example is a pilot simulator, or we can say that a flight simulating environment, right? So how does a pilot is going to learn how to fly an aircraft? So before driving an actual aircraft, it is very, very important to train the pilot for different situations. And this is kind of an aircraft simulator for a pilot where they will learn how all the control and commands or how all the inputs are working and what kind of behavior we are getting in the aircraft and how is the visualization as well, right? So here what you see is the actual inputs, and these are physical inputs. You might have seen a driving car simulator like this, right? And this is nothing but a screen where the driver is going to experience the external environment, right? So once these inputs are fictitiously provided in this simulation setup, the aircraft is going to behave accordingly and this view will also get affected. So there may be some alarm indication, there may be some other communication related things, but overall this simulation is going to help pilot learn about how to fly an aircraft, right? This is going to be the very, very important phase for a pilot before driving an actual aircraft, right? So how you come up with a learning? So learning is going to be the basic outcome of a simulation, right? So here a pilot learns how to run an aircraft. If you have a proper mathematical model, something like this, you will also learn how a system behaves and what kind of input will result in which kind of output. So this is all about the basic understanding of simulation. So here, let's understand what is a block diagram approach. So once you have understood the model and the simulation, now we need to understand what is the block diagram. So block diagram is nothing but how you create your model mathematically. So block diagram is actual representation of your system in a block diagram way, right? So logical operations, right, or any other equations, right, are converted into blocks. So let me give you a very basic example where, let's say, we have two variables A and B, right? These are the two inputs available, and our process is going to add these two inputs, and finally the result is going to be stored in another variable called sum, right? So if I write an equation where sum equals to A plus B, where A and B are the inputs and sum is the output, this very simple equation can be represented in a block diagram as well. So how do we make a block diagram? So let's say these two are actually the inputs. The plus is an operator where we need to do that operation, and finally we need to assign whatever is the result of this process to a variable name as sum. Now how do you do it classically? If you have learned Matlab scripting, you will be writing a very simple script that sum equals to A plus B provided A and B are declared. Now how do you perform the same task in a block diagram way? Let's see that. So if you have not learned about Matlab scripting, if you are familiar with let's say simple C program, your simple C program will be looking like this, right? So you declare two variables, for example x and y in this case. So x and y are declared and the sum is going to be the result variable. Now you may ask for the user input that you enter two values of x and y. Now once the user has given two values, you are going to make sum of two inputs, and that is going to be stored in a variable sum. And in the printf command or print to the file command, you say that sum is this value, right? So whatever is this sum is referred over here and it will be taking this place. So in this simple C program, how can we convert this into a block diagram, right? So instead of writing a text or instead of following a syntax, can't we represent or can't we just focus on what is the process to be done instead of how to take the input, how to print the output? If we just focus on what is to be done with the inputs, it will be much easier, right? And therefore the block diagram approach is actually a very simple representation of a complex system, right? So here we are taking just two variables. It may be any complex situation or a system, or maybe any complex equation. So if I convert this C program or maybe a Matlab script of adding two variables into a block diagram, a Simulink block diagram will look like this, right? So for example, here we have the two input blocks and they are declared as a constant and their values are, let's say, 23 and 45. They are predefined, and we have a block called add which is going to accept these two inputs, and whatever is the output that is available at this port, and that is given to a display port like this, right? So this is one simple translation of the equation into a block diagram way. So this is the block diagram approach. Now how this block diagram works, or what are the things related to this? How do we run this block diagram? How we can change all these values? Can we have a third input as well, right? Or instead of this, if you can vary all these parameters while the simulation is running, and instead of a display of a constant number, can we have a graph available? Yes, everything is possible in a Simulink environment. So this is just a basic example to start with. In fact, Simulink has all the powerful mathematical tools such as minimum and maximum or real imaginary number system to complex number system as well. And there are so many other similar basic mathematical functions. So instead of just adding a number, if you want to find out what is a minimum and maximum value in an array, right? So now this is a constant. We can declare an array, or let's say a group of numbers, and they are assigned some value, right? So let's say here you have some array representing the temperature data from a temperature sensor, and you want to find out how much was the maximum value in a typical duration of time. So let's say you run your simulation for 10 seconds and you try to figure out in the 10 seconds with the all previously inputted values which one is the maximum value. And let's say in 10 seconds you are going to input 1000 number of temperature value data or temperature samples. So when this 1000 number of temperature samples are given to this block is basically going to find out which value out of this 1000 value, which value is the maximum value, or similarly you can find out the minimum value as well. So this minimum and maximum block, instead of writing an script which may be a tedious task or which may be time consuming if you are not a programmer, then it's very simple to add just a minimum maximum block, and that block is going to be nothing but maybe your 5 or 5 to 7 line of codes, right? So this is how modeling in Simulink works, and this is how the block diagram approach is deployed for Matlab and Simulink. So once you have figured out what is to be done, right, you can actually do many more things, right? So what is the difference between the programming language and a block diagram language? So here, in case of a programming language, if you are not a good programmer, what you will be doing ending up, or what you will be spending most of your time in the syntax, right? So probably if you are new to C program, you will be learning about how to create variables, how to declare them, how to ask the user for input, how you can do the assignment and addition operator, those are mathematical operations, how for let's say this using of scanf and printf, you may require to include some header files over here. So how the scanf and printf are defined, and how exactly if I do not write some typical syntax like %d over here, then there will be some errors, right? So instead of focusing on writing a program and following the syntax, you can just focus on what is to be done with the inputs, right? So this is how the block diagram way is going to simplify your calculations or simplify your complex systems. Now let us learn about model-based design for engineering systems. So what are the model-based design of an actual engineering system? So mathematical models are most suitable for initial experiments, right? So for example, a mechanical engineer has decided to actually make a gearbox, right? So you are going to make a gearbox, and you have an input shaft and you have one output shaft coming out of this gearbox. Now before you actually go and manufacture, or maybe you take some help of the technician or the person who is going to make you this gearbox available, or maybe they may be making one prototype for you, it's very important to do some initial experiments without the actual gearbox, right? So mathematical model is going to help you, or it is going to be most suitable for very fundamental or initial experiments. So what you are going to do is basically you will be trying your concept, right? You will be actually doing your proof of concept kind of thing, or you will try to understand what will be the loading arrangement. Let's say what are the values of the speed and torque, what can be the size of this gearbox, what can be the type, right? So you may be interested in deciding the size, or maybe deciding the type, or maybe what is going to be the overall efficiency, right? So for this you must start with a basic mathematical model. So sometimes the actual system realization may be costly and time consuming, right? So you may do various number of experiments with different size and different type, but you may not actually manufacture all of your concept, right? So once you have a very foolproof concept or very well tested concept in a modeling and simulation environment, then only you will go for realization, or you will go for making one, right? So the actual system realization may be costly and time consuming, right? And some experiments are always better to be done in a simulation mode, right? So for example, a vehicle crash test, right? So vehicle crash test is one such example where you will always like to be avoided, right? It's always better to be done in a computer system, right? Because it may be costly, it may be time consuming, and it may result into the physical damage, right? So you would like to avoid any physical damage, any usage of the energy. You may not want to take any risk, right? It may be risk, financial risk, or it may be the safety related risk, right? So for example, one electrical engineer is required to do a short circuit test, right? He wants to, let's say, test a circuit breaker, or let's say a protection device, and he wants to try that whether this protection device will work on a short circuit or not. So actually he can implement this in a model based system design, and he can visualize the results in how much time the faulty part of the circuit is isolated, and what is going to happen if the fault is going to be persistent, or if the fault condition is not recovered. So model based design is going to help engineers do all these things which are actually not possible physically, right? So there are many advantages of doing such analysis or doing such initial experiments within your computer. So this is the advantage of model based engineering system design, and actually the model based design can be interdisciplinary, right? So for example, you want to analyze this gearbox for a DC motor, right? So here a DC motor is this block which is going to drive this shaft, and there is a gearbox, and there is some mechanical load connected over here, right? So you want to analyze what happens to the motor as well as the gearbox once some kind of load is applied on this shaft. So you can run a simulation which involves both the dynamics of a DC motor as well as the gearbox. So these are the advantages of model based design. Let's go further and understand more about fundamental elements and using the mathematical model of basic blocks of electrical and mechanical system. So what are the basic elements of electrical and mechanical system? So let's say the fundamental terminologies or fundamental elements, or I will say the fundamental components of an electrical system are nothing but a resistor, a capacitor, and an inductor, right? So similarly, a mechanical system can be also realized by a spring, all those components which are having some typical kind of a behavior that may be called as a spring, or they may exhibit some kind of a spring behavior, a mass, and a friction component or a damper component. So these are three fundamental mechanical engineering components or elements, and resistor, capacitor, and inductor are very fundamental electrical engineering components. So this actual elements are very useful in building any such larger system. So this inductor, capacitor and resistor may represent a circuit of a radio transmitter, or it can represent a circuit of a FM receiver, right? Or it may represent a circuit of an antenna. So a resistor, inductor and capacitor are three building blocks of electrical and electronic systems, while spring, mass and damper are very fundamental mechanical blocks. So these are the three systems. Now if we want to, let's say, start modeling about a resistor, right? So let's take up a symbol of a resistor, and let me give you some brief idea about electrical system. So if you apply some potential difference, this is called voltage between two terminals, and if there is a potential difference connected across any of this element or a group of this element, the current is going to flow according to their behavior. So voltage and current are one such system, and similarly here you have the force and velocity, right? So force and velocity are let's say two mechanical engineering phenomena. Voltage and current are electrical engineering phenomena. Now let's try to have some mathematics of all these elements, right? So let's say I want to model the effect of a resistor when some voltage is applied across it, right? So I'm going to connect a DC supply source over here, and I'm going to make the circuit closed. So this is the V voltage, R ohms of resistance is connected between these two terminals, and current I is going to flow from positive battery terminal or positive DC voltage terminal to the negative DC voltage terminal. Now from the fundamental laws like the Ohm's law, right, you can decide what is the relationship of voltage and current and the resistor. So resistance is such a phenomena or such a parameter or an element in electrical engineering which is going to make the voltage across this device which is proportional to the current flowing through this, and that constant of proportionality is replaced as R value. So the voltage across this resistor is I times R, and this is a very fundamental Ohm's law, or we can say this ratio of voltage and current remains constant, right? So you might have done a very fundamental experiment in your laboratory in a school where you have a resistor and you change this voltage. You have a variable DC voltage source and an ammeter connected in the circuit, right? For example, like this, and this ammeter will help you to read out the current value, and if you keep on taking the ratio of the voltage and current, it is going to be remaining almost constant, right? So for a constant value of a resistor, if you do this reading where it's voltage V1, then you apply a slightly higher voltage V2, you go with the voltage V3, and you have a corresponding current I1, I2 and I3, and if you take this ratio V1 by I1, V2 by I2, V3 by I3, they are all going to represent almost constant value, which is the resistance R. Now provided that due to the current, the temperature of the resistor remains same, right? So the temperature parameter of this resistor remains same, then the Ohm's law holds true. Let's take a similar mechanical engineering example. So let's say this is a surface, and on this surface we have some object kept of mass m, and if you apply some force F in this direction, it is going to get accelerated with some value, and that fundamental equation can be represented as F equals to mass m into acceleration a. So this is a very fundamental Newton's law where it is applied to the mass kind of a fundamental element related to mechanical engineering. So now if I want to write this simple equation in terms of the position, right, and let's say a velocity. So we have A equals to dv by dt. V stands for velocity. This is going to be simple like rate of change of velocity with reference to time. And if we do the change in the position of the object, right, how much is going to be the change in the position of this object in this direction, that can be represented as d square x by dt square, where x represents the position variable. So this is going to be a differential equation of second order, and the similar equations are available in electrical engineering for an inductor as well. Now, instead of using all these equations and making the effect of the temperature, or let's say making the friction where it is present with this surface and the object, we can actually model all this equation in a block diagram way, right? So instead of writing all these equations, if we have a block of a resistor along with this symbol, it will be very easy for us to visualize and understand what this system is about, right? So the Simulink offers such blocks or such symbols where you have the resistor implemented in terms of its resistance value, along with let's say, for example, you want to implement some temperature effects, or all the inductors and capacitors along with, let's say, some initial conditions. So these are the fundamental elements, and you will find all these blocks in a Simulink environment which are exactly like their symbols. So this is a symbol of a capacitor, let's say this is a symbol of an inductor, and this all readily available blocks will help you to simulate an RLC circuit. So for example, you want to start your filter design and you want to see the effect of applying this small DC voltage to the RLC series circuit. You can actually connect a circuit like this, and you can make an model of an electrical circuit. At the same time, you can make the model of a mechanical arrangement as well. So for example, if you have a suspension system, it can be represented by a spring, mass and damper, and you can have a detailed mathematical model of a suspension system using this fundamental mechanical blocks. Now with this, let's now move on to the Simulink environment. So what is a Simulink environment? So a Simulink environment is going to be a block diagram environment, and let's say we want to make a fundamental use case of a pump, right? So we want to analyze, or we are interested in doing a simulation or doing some experiments, or try to understand or learn about the behavior of the pumps. How we are going to do it? We can make a block of a power supply. And why do we require a power supply? Basically the pump is going to be motor driven, and this motor will require some power supply. So this motor has to be also controlled. So let's say we have a motor drive system or a motor along with its controller, and on the shaft of the motor you have a pump connected. And yes, obviously there are some pipings over here, right? There may be some user inputs over here, and there may be some electrical protection related circuits at the power supply input over here, but you want to create such a setup which is as real as a pump. So this is the arrangement of a pump along with a motor drive, right? So this is a motor driver box, and here is what you see, a motor in a green color, and this is what is a pump. Now what you need to do is you need to connect some piping over here from this part, right? Now we want to learn about such a system where it's electromechanical or a motorized system. So we can actually simulate the full system where we not only have the three-phase electrical supply or three sine waves 120 degree apart from each other, but you can also implement what is the type of the control, what are the user inputs over here, and what is the type of the motor. Let's say this is a simple DC shunt motor, and let's say there is a gear ratio over here between the motor shaft and the pump, and this motor is controlled to control the flow rate in these pipes. So the entire setup can be visualized, or we can make it in a Simulink environment. So Simulink environment is basically a graphical environment where you will have all such blocks which will represent the graphics. So let's say, for example, if I want to have a single phase source, I'm going to have a block called a sine wave or a single phase supply, and it will look like this. So all the symbolic representations are going to be there. In mechanical engineering, let's say if this is going to be a gearbox, and there will be a similar system which represents the driven shaft and the driving shaft like this. So this may be a representation of a simple gear system. So a graphical environment is going to help the user understand about what exactly this symbol represents. So it's a graphical user interface. In the back end, or let's say in the background, how the simulation is going to work, that also we will be studying. So here it's a single phase sine wave, and what you can do is you can configure for this value and frequency. So you can assign phase, frequency and amplitude, and if it is a gearbox, you can assign let's say the losses happening in a gearbox or the gear ratio. So this is going to be a graphical user interface where you click on this block and configure these parameters, and simply once you have done the configuration, you close the configuration window and simply hit the run button, and this sine wave is produced and given to the external circuit. So this is how Simulink is going to work. So what are the blocks going to represent? Simulink is going to have many number of blocks, and all the blocks will be representing either of these 3 or 4 systems. So they may represent the entire physical system, or it may be a part of a subsystem. It may either represent the signals, or it may represent the mathematical function. So you may have some block representing the physical signals like the velocity, or like it may be angular velocity or linear velocity, or it can be the voltage and current, which are physical signals. These blocks in a Simulink may be of a subsystem which will eventually form a larger system, or it can be a simple mathematical functions similar to what we have seen as the add block. So this Simulink blocks are going to be representing various types, and ultimately they are nothing but some sort of equations in the background, and in the GUI case you just have to configure them, right? So let's say this is a single phase source, and this is going to be a mathematical function of sine omega t plus phi. So where you have to assign some peak value, let's say a, you have to assign the frequency, and you can add it, or it can be a plus or minus system. It can be a phase. So this a is going to represent an amplitude, and this equation will be implemented in the background to simulate this sine wave. So this is about the Simulink environment. So now let's discuss about the pump application a bit more in detail. So what is a pump application? So the pump application involves both the system which is electrical and mechanical, right? And it may be involving the hydraulics, or it may be involving the protection from the electrical side. So a pump application is going to have an electrical supply which may be a single phase or 3 phase. Now this electrical supply is going to be of fixed voltage and fixed frequency, and if your motor is going to be DC, you will be required to convert AC into DC, or some sort of converter or a controller is required in between the electrical supply and the motor. So electrical supply and the motor is going to form altogether a electrical system. Now on the shaft of the motor, what you may have is some gear ratio with a gearbox and a pump. So the G block and the P block represents the gearbox and the pump. Now you want to simulate what happens when we give single phase 50 Hz 230 volt RMS supply to a DC motor with an AC to DC converter, and where the pumping flow rate requirement is X amount of liters per minute. So in, let's say, 1 minute, this much amount of liter of water is being pumped, right? So this is your flow rate requirement, and you may convert those flow rate requirements into the motor speed and torque requirements, and you may be interested to analyze how much is the energy flow. So what is going to be the energy flow if the AC to DC converter efficiency is efficiency 1, the motor efficiency is going to be the another set of efficiency 2, the gearbox is having another efficiency 3, and efficiency 4, right? So if you model all these parameters in detail and you want to find out how much is the energy consumption, you can actually put some measurement device on the input side of a supply, and you can realize what's happening inside. So this is a pump application, and you can make a Matlab model which will be exactly replicating this situation, and you may actually try with the built-in model of a DC motor or an AC motor. In case of an AC motor, if you want to convert this into fixed voltage, fixed frequency AC to variable voltage, variable frequency AC, or you may wish to try some different kind of gearbox, or you may wish to try some different configuration of pump. So all this is possible in a Simulink environment, and it's going to be very quick. So you can analyze and study your system using Simulink starting from its beginning to the end. So the full system can be analyzed like this. Now you may have some questions related to, is the mathematical model same as actual system or the actual model? So if you see this image, right, this is the actually a render image, or let's say a 3D model which was created by the civil engineers or the architects, and this was the fundamental concept. And when they created the building, or this is going to be a 3D concept kind of a building, and this is going to be a real one. Now the concept may be something different, and the real might have some different behavior, right? So the answer of this question, whether the mathematical model represents the actual behavior of the system, the answer is both yes and no. So it may be almost similar or may be exactly similar, right? So for example, an electrical engineer wishes to try to understand the behavior of a resistor along with the change in the temperature, right? So this is a resistor, and you have the set of values of temperature T1, T2 and T3, and for all these three values you want to have the different values R1, R2 and R3, and you want to model, or you want to understand what exactly happens when you apply some 100 of voltage to this resistor. Now when you do this experiment in reality, it may be exact or it may be having some errors. Now what are the parameters? What is going to decide whether the mathematical model which we created is going to be accurate or not? So there are many parameters, and it depends on the level of the model, right? Or it depends on how deep is the modeling exercise done, right? And that is another term is called a fidelity, or let's say the quality or the degree of the model which is used. So the accuracy or the nearness to the reality represents the model level. So accuracy and dynamics are based on the assumptions, and one model may be accurate in one case but may not be in other case. Let's say for example, this building is from the look point of view is similar. From the loading point of view, let's say all these buildings are going to have certain amount of load applied, and that may be also matching. But when it comes to, let's say, earthquake test or a dynamic test, this model is not going to have sufficient details, right? So one model may be accurate in one case, but it may not be accurate in other case. So what are the difference between mathematical model and the real system? So what are the factors affecting this, right? So all those assumptions when you made while creating the model, all those initial conditions, and all those actual environmental and other effects. So if you consider all these real systems, your model may be as real as the actual system. So if you consider all real world inputs, right, where it's all is very important, and the real world inputs. So if your model is taking care of all real world inputs and its behavior, then you can model your system perfectly. So how does it work? So how do you actually create a mathematical model? So mathematical models are created with this exercise. So first you do a physical experiment, or you do a practical, right? And from the practical you decide about the governing equation or a theory. Let's say, for example, a simple Ohm's law where the voltage across the resistor is proportional to the current passing through it, right? So this is a physical experiment, and from that experiments the scientists have decided, or scientists have come up with the governing equations, which are called theory. Now all these theoretical equations are solved in a graphical environment like a Simulink, and the mathematical model is created for a simulation, right? So this is the way how it works, right? So what kind of governing equations, what kind of inputs, right, you are taking on, what level of equations you are implementing for a mathematical model, that will decide the fidelity or degree of or nearness of your mathematical model. So I hope you will be now clear about the question whether the mathematical model are real or fictitious. So in some cases it's very difficult to realize them in terms of the mathematical modeling. In that case, what you are going to do is you take the actual practical data from your experiment and you feed the data to your model, right? In that case, your simulation is going to be perfectly represent your real system. So it's now the time to have a look at the Simulink. So let's go to the Matlab and let's have a first look. How does the Simulink look like? So once the Matlab is installed in your machine, you can click on the menu link and start the Matlab. So you might have a desktop shortcut, or you can start Matlab from the command window. So this is the default view of the Matlab window. What you are able to see here is the options on the top, a command window in the center, the current folder in the left side, and workspace in the bottom left. So here, so what you see on the top side, these are the options to configure the Matlab environment. So here you can actually make a new file. It may be a new script file or a model file. You can make a new folder, or you can find something in the file. You can import the data. You can save your workspace. You can analyze and run your code. And here is a Simulink button. So we are going to actually use this Simulink block for our further analysis. Let me click on the Simulink block and let's see how does the first screen of the Simulink looks like. So when you click on the Simulink block, it will come up with a Simulink start page. So once the Simulink start page is going to pop up, you will see some options on the left side where you can open any Simulink model which is pre-built. You can make any projects, or you can start learning as well from this side. Now the new file has so many options so that you can create a new model, or you can create a subsystem which is part of a bigger model, or you can create a library files as well. We are going to see all these options as and when it is required. If you scroll through this, you will be able to see many block set and toolboxes where ready-made templates are available. What is a template? A template is nothing but a basic file where you can start your modeling. So a template is going to be pre-built, and you can actually use this template. Let's say, for example, you want to start with a hydraulic system, and if I create a hydraulic Simscape model, then a basic template or blank template will open up, and which is responsible for helping you to create a hydraulic model. So here you will see many other options, and while this is creating the model or a template, this is how it looks like. So here you have some fundamental input blocks, some conversion blocks, and some display. So there is a by default configuration, and this model is ready to run, and here you can have all Simscape Foundation hydraulic resources available at your fingertips. So this is called a template. It's a blank one, but you get some minimum inputs and outputs and configuration related to hydraulic kind of system modeling. So let's go through first a very blank model. So I'm going to create a blank model, and this blank model is this window. So now, for example, if you are new to this Simulink window, let me explain you all this part. So here what you see in this highlighted blue block is the simulation, how you can save your simulation, you can print, you can have a Simulink library browser. This is what we are going to explore in the very first look. And there are many options like debug, modeling, format, and apps. Apart from that, here you have an important window where you can have very related buttons to simulate your model. So once your simulation is built over here in the blank area, you can configure, run, stop, and forward or step back. And there are other options of logic analyzer, data inspector, and other things as well. So what you see here is a blank model, and first of all we may require to save this model in a typical file. So let me save this model, and we'll name this as first model, right? So I'm going to name my file as first, and look at its extension, look at its save as type. So these are Simulink models called SLX. Now there are another options where in the previous versions of Matlab and Simulink you can save your file as .mdl as well, and that is a model file. So these are the two extensions possible. Let's save our first file in first.slx format. So now my file is saved. I want to create a basic arrangement, or let's say a basic situation where we want to understand how does a Simulink work. So for that, how to add the blocks. So for adding the blocks, we need to have a look at the library browser. So this is the icon which represents the library browser. So if I click on the library browser, you will be able to see what are the all installed libraries available as Simulink. So this library browser is actually data set or pre-built models inside the Simulink environment. So we just have to drag and drop this models which are available in the library and connect them in our model. So if I show you how does a library browser look like. So what you see here in the left part is all different toolboxes and the block set. So what you see as a basic Simulink toolbox, the aerospace, and these are arranged in the alphabetical order. And you can see data acquisition, embedded coder, you can see the powertrain block set, sim events, Simscape, communication toolbox, etc. So right now we have opened the Simulink block set, and in that we have all these options which are again listed over here, right? If I click on the commonly used blocks, so here we have a commonly used block, let's say a bus creator, a bus selector, a constant, a product, a saturation, scope, sum, etc. Right? So these are very commonly used block, and I can simply drag and drop. Let's say, for example, we want to make a product, right? So in the earlier session, we know we have discussed that what is going to be a Simulink block diagram look like. A Simulink block diagram is nothing but all the equations in the form of the block or in the form of a graphical representation. So here, now you can see I have added a product block. So, and it shows X or the symbol of product in the middle. Now, what we need to do is we need to take two inputs and one output. So this is a block where it is going to take two inputs, one from this side, another from this, and there will be a third output. Right. So these are the lines or signals which we are going to connect with. So what we need to do, let's have some constant numbers and do the product, and let's run the simulation and see the result. So basically it is as equal as you are writing a program for multiplication of two numbers. Now it's important to learn how we are doing this, right? So let me take two constants, and the moment I'm placing the constant in my model, it will ask me for what is the value of the constant, right? So let's say the value of the constant is 12.3, and I'm dragging it over here for a better connection. Now Simulink offers a very good way of connecting the signals where I need to click this. Now there are two arrows which are highlighted in the blue color. If I just highlight connect over this, it will be automatically connecting to this line. I can arrange the blocks and those lines will be arranged automatically as well. Now if I want to create another constant which is another input, I can just right click on this and make a copy of this. Now in order to change the value, I can change it from here itself. Let's say this is 4, and we can connect this to this line. So now we have two inputs ready to be multiplied. Now what this block represents, these are very simple thing, but how do we configure this block? So if you double click on this block, it will show you what is this, right? So it is going to explain you that what this block represents. It is going to output the constant specified by the constant value. It is also possible to represent this as one-dimensional vector array, right? So you can have multiple number of values assigned to this as well. You may provide signal attributes and what are the minimum and maximum values, which we will see later on. So right now, whatever I have entered 1, 2.3 or 12.3, that is assigned as a constant value. And if I change it from here, we can actually, the same will be reflected here as well. So these two are the constant blocks. Let's say, let's multiply with 3 instead of 4. So here you can see that it's changed to 3. This is a product block, and this is a multiply or divide the inputs. So how we can use this block, that is explained over here, and what kind of multiplication you want. So you want element to element multiplication, or you want a matrix multiplication, that you can check from here. Because right now we are doing a simulation with one constant number, it's going to be more simple. Now how do we visualize the output, right? So let's say we are going to get some product output and we want to visualize the output. So another way of adding the blocks is directly double click over here anywhere in the model, and it is going to ask you, or it will be searching for the blocks, right? It is as equal as dragging and dropping the blocks from Simulink library browser. So instead of finding it in a library browser and there are so many other blocks, it may be better for you to quickly search out some display related block, right? So let's say we want to just display the output number. So I'm going to write display. So when I write display, there may be various types of display available. It may be Simulink dashboard display or a very simple display like this. Now this display is going to be let's say connected to this line, and when you have the line connections are easy and you can make it like this, you can just click on this part. All other possibilities of connecting this will be highlighted, and you just need to hover your mouse to this block and the connection is made. Now what are the properties of the display, right? So the decimation point is 1, and you may keep it like a floating display or you may keep it unchecked, right? So if the input signal is going to be a string, or there are many other data types which we are going to learn, then this will be displayed in a different way. So right now, what is the format? It's short format, right? And if you have learned about the data types in the script or maybe any programming language, you know what is the meaning of short, long, bank, hex, or binary or decimal, right? So let's keep it the default value short and let's run the simulation. In order to run the simulation, you have to use this panel, and you can actually use all these blocks in order to configure your simulation time. So this one being the very simple one, Matlab is not going to take much time in making a product of two numbers. Let's keep the simulation stop time as 2 seconds. Now if I press run, this will be displaying the output on display part, right? So this is the output which is available to us, and this is very simple model which we have created. You can actually create other different types of models as well. Now before you create a better model or maybe a fairly complex model, let's have a look at all the elements. What are the tools which a modeling engineer is equipped with in a Simulink environment? So if you go to the library browser, so we are going to now have a look at the library browser. So my screen is now showing the library browser, and here we have all different categories in the continuous category. So Simulink is a basic fundamental, and there are continuous, dashboard. So what is the dashboard? So dashboard is something like it looks like some lamp. It may be a knob, it may be a push button. So these are graphical user interface based GUI, right? So in a typical control room, when an engineer is sitting, they will be dealing with some kind of knob, some kind of gauge outputs, some kind of displays, some kind of rotary switch, right? Or maybe a toggle switch. So these are the dashboard related inputs. Now there are continuous block where you can use the integrator, where you can use a PID controller, you can assign a transfer function, you can have a delay signal, or you can do the derivative. And there are discrete blocks as well, which are nothing but representing the same blocks in a discrete environment. So remember, these are very fundamental blocks, and using this Simulink fundamental blocks only, there are many higher order or complex system blocks are created in all these toolboxes. So in order to work with a Matlab, you need to be thorough with the fundamental mathematics of your problem. So whatever you are trying to solve, you must be knowing that, right? So if we, for example, see that let's say absolute value, right? So it's going to be a mode operator where even if you give some negative values, it is going to turn out into a positive value, its equivalent positive value. So here you have a complex to magnitude and angle. So you give a complex number here, let's say 3 plus 4i, and it will give you the real part and imaginary part, or the real value and the angle, right? So here these are many blocks. So here you can do the subtraction as well. Here you can take the sign of some number. Here is a product which we used recently, and there are many other blocks like a math function. So in fact, I can open some of the block here itself and understand what is the meaning of that. So it is going to take the exponent of the input, right? So mathematical functions including logarithmic, exponential and power, these are the functions which will be taken, right? Here it won't allow you to see what are the options, but when you add this block into your model, then you will be able to modify these blocks. So for example, if I want to add this, I can simply right click and add block to model first. So first is the file which we have just created and saved. So now this block is added. If I go to the first, now here we have a math function. Now if I double click, now I have a possibility to choose which function we are using, right? So you can take a reciprocal, you can take a power or square. So whatever is the input, that its square will be given in the output. So whatever is the input, its exponent will be available in the output, right? This is as equal as writing a script where you have various mathematical functions, right? So instead of writing a script in a Matlab environment or maybe other programming language, the block diagram is going to make your task easy, where you focus on creating the system level model and not the actual program. So let us see few more blocks where you have something related to sources, right? So here are the sources which we have used a constant value. Now instead of this, we can use the ramp as well. Now what is going to happen if we have a ramp input instead of a constant? So let's do it. So I'm going to use a ramp, and let's try to use ramp in our case. Now I have added this math function and I'm not going to use it. So I can select this and just make it disable, and that is possible by comment out. And it is also possible when you just do click on this 3 blue dots, and you can just like do the comment out. If you have not comment out and you are not using the block, the Matlab compiler or the model translator is going to give you an error. Now, so instead of multiplying with the constant, so let me not use a constant, let me use a ramp input. So what is basically a ramp? It shows in a signal like this, its value is continuously increasing with the time. Now, what is the value increment, right? So let's say its slope is 1. So at every second, its value is going to keep on increasing by 1. So now if we do this, what we are going to have in the output is not a constant number, but we will have a multiple numbers, right? So at every second, its value is going to be updated internally, right? This is as equal as running a for loop and increasing a variable whenever every for loop is executed. So let me run the simulation for a slighter longer time duration, let's say 10 seconds. Now, what are the expected output? What we will be able to see in the output? So at the end of the 10 second, whatever is a display, that will be updated here. So let me run this simulation and let's know what is output. So why we get 123 in the output? Because we are running the simulation for 10 seconds, and at the end of 10 seconds, because the slope is 1, we are getting the value of this block as 10. So now this is just a display. Now instead of a display, let me see all these values on a scope. So in order to use a scope so that we can have a record of all the previous values as well, so I can connect the scope over here, and I need to see, instead of a display which is going to be updated at the end of the simulation, we want to see what has happened as a plot. So what I can do, I can just right click over this signal and connect over this line. So now I have connected the scope. Now if I double click on the scope, will it show the result? No, because we have just connected the scope and the simulation is not running, right? So I have double click on the scope. Here you see is nothing because simulation was run previously, not after adding the scope. So any modifications you do, you have to make sure that you run a simulation and then view the results. So this is a very simple way of creating the first model, and it's always advisable that you save your models as well frequently. So whenever you click on the save, this model will be saved on the hard disk and the star arrow will disappear from its name. So if the star arrow still appears, which means that there are some unsaved changes. So now what kind of output we are going to have in the scope? So in the scope, our output is going to vary from 0 to 10 seconds. So if I click on the run, my simulation is finished now. And if I click on the scope, here is what you see in the output. So this yellow line indicates the output at each time duration. And this is nothing but 12.3t, right? So whatever equation we have implemented is nothing but 12.3t. So here I have created a very fundamental simulation of 12.3t. So Simulink block help us to actually create some text file also, which is relevant to this model and which is not going to be executed. Like this block which is commented out, we can make some annotations as well. So if I double click anywhere, instead of searching any block, if I click on create annotation, it will ask me to type any text. So this model is for 12.3t, right? And let's say our output is y, and y equals to 12.3t. So this is what we want to define as description of our model, and this can be also changed to a fairly larger text, so that next time you open your model, you will be able to understand easily what this model is about. So you may have some help related stuff over here, or you may have some your assumptions here where you want to say that 12.3t, and if instead of a ramp of 1t, if I like have a 2t, so I can write 12.3 times 2 times t, right? So here you created your very first model, and while you are learning, I will recommend that you will try yourself that how the Simulink works, and you try making simulation as well. So now let's go back to the Simulink library browser and understand what are the advanced level blocks. So we are going to straightforward focus on the electrical and mechanical systems, because there are so many other block set which are like aerospace, which are related to communication, which are related to instrumentation and control. So let's go to the Simscape, which is again an electrical and mechanical library. So let's visit some electrical components over here. So here you can see the electrical components. Here you have the connectors and references. So you have a ground connection, which is a reference point. Here you have an open circuit kind of a situation. Here you have a phase splitter. Then you have electromechanical stuff. So electromechanical is nothing but the motors. And you may have a very fundamental actuators as well, right? So here you may have different types of actuators which are solenoid. So let me add this to my block. Now my block is fairly simple, and we have added a solenoid over here. And what you see over here is not exactly the simple block, but you have some graphical images, and there are more than 2 inputs, right? So here you need to connect positive, here you need to connect negative, and these are R and C, which are the mechanical part of a solenoid. So if you are aware of how a solenoid works, basically you need to give some DC supply, and this DC supply is going to create a magnetic field, and this R and C will be showing some mechanical movement. So this is a solenoid block, and basically you can double click and configure this for your model. So now the models are fairly complex, and here you can read about the description. What is the magnetic force? What are the mechanical output? What is the spring constant? What is the damping? And how much is the stiffness? So once you have done all these things, you can actually play with a solenoid system in your model. So this is about one library, and you will be able to see many different asynchronous and brush type motors. This is a very simple DC motor, shunt motor, or a universal motor. Let's see some mechanical blocks. This is Simscape category, and here you can have another category called drive line. So in the drive line, you will have all the things related to automotive related things, and here you have multi-body and fluid related systems. So here you can have hydraulics, body elements, let's say some constraints. These are a variable mass model, a solid cylinder, a file solid, or maybe an inertia block, or forces and torques, right? So here you have very advanced blocks like spring and damper force, right? Now, how do you learn about a basic element, right? So basically you can actually learn about any block from the help menu, right? So let me try a simple resistor for electrical systems. So a resistor is nothing but a component which follows the Ohm's law as per our discussion in the first part. So if I click on this, now my resistor is available as a model. Now I want to learn more about this, and I want to get some more help. I can insert the resistance value over here, and I want to take help on what is this resistance. So there is an excellent Matlab documentation available in order to explain you how this model works. So this documentation will help you what are the fundamental governing equations which we have talked in the previous session. So those governing equations, in this case, a linear resistor follows the Ohm's law, where voltage is equal to I times R. And what are the all behaviors? What are the other parameters? Let's say you want to implement a variable resistor. So here voltage is equal to I times R, and the R value can be updated by some external parameters, right? So let's say you want to implement a temperature dependent resistor, you may try using this one. And what are the ports? What are the parameters? They are all explained over here. So the Matlab documentation, in this tab, you can see that there is Explore Matlab, Explore Simulink. And if you click on Explore Simulink, you will be getting step-by-step process how you can get started, how you can do the modeling, what are the parameters of the simulation, how you can do the project management. So this is about the Matlab help, and let's come back to our first diagram. And in fact, I can do the zoom in and zoom out by the scroll of a mouse. So let's say we have done a very fundamental equation in our first model, and we want to save this, and let's say if we do not want all these models, we can select them all and delete. And if we, let's say this is also of not use, you can keep it commented out or delete. So this is going to be a fairly simple environment where you drag and drop all your blocks and just hit the run. So this is about the introduction to the Simulink. Let's start a new session with the Matlab and Simulink. So if you remember, we have seen a new file and we saved it with the name first.slx. So here you will see the current folder, and in the current folder you will be also seeing which file we have recently saved. So this was the first file we created and saved it on the computer. Another important thing to remember is what is the directory path. So whenever you open up the Matlab, it's very important to check the directory path, and then whatever files you have, that you can open it in the Simulink. So let's start a new session again, and for that you have to click on the Simulink button again. I'm showing you this. There is a Simulink button here, and it's also possible to type Simulink and run it. So another way is you can type Simulink. If you are good at writing the scripts and you are comfortable with the keyboard, it's also possible you can give a command Simulink and the Simulink will start. While the simulation is taking time to start, let me show you another important part is the help. So when you click on the help part, you will be able to see the overall Matlab documentation, and this documentation is going to be of your all included toolboxes. So at the time of installation, whatever toolboxes you have added, all those toolboxes help will be located here. Now the Simulink is available. If you see here also we have a recent file, the first.slx, or you can also create a first blank model. So let's create a blank model, and now we are going to start learning about how we can actually add some of the higher order, or let's say some of the complex blocks, and how adding of this complex block will change the environment in the Simulink. So the other important thing to remember is the Simulink library browser, which is here. So when you click on the Simulink library browser, it will help you to view all the blocks together. So now I'm opening the Simulink library browser, and in the last session we have seen how to use some of the blocks where it's addition or multiplication and a display and some other blocks. So here, when we have the Simulink library browser, let's know which are all these blocks available in the Simulink and what are the options as a modeling engineer with you, so that you can add mechanical and electrical blocks. So if you see here, there are so many blocks included, and when you click on this, they will get enlarged, and all those what are included in the selected block. For example, right now the continuous is selected, and all those continuous blocks, they are displayed over here. So whichever category you are going to select, for example, I'm going to select a powertrain block set and the drivetrain. So all those drivetrain block set will be appearing over here. So what you see as all these blocks are actually the larger level or high level model of automotive systems, such as planetary gear or torsional compliance or disc clutch and some other models. So this is about how you can get the higher level blocks, and you can take your time and have a go through this all block sets. And another important block set which we are going to focus on is going to be the Simscape. So what you see here is a Simscape, and in the Simscape you will have all electrical and mechanical physical blocks. So Simscape is nothing but the modeling of the physical systems, which means the actual systems in a Simulink environment. So if you click on the foundation library, you will get the driveline and electrical and mechanical foundation libraries. So here are the foundation library of the Simscape. And if I click on, let's say, a mechanical, so in the mechanical system you will find the ideal force sensor, rotational motion sensor, ideal torque sensor, and there will be some sources. What is the meaning of sources? The sources are nothing but the actual creators of the force, right? So for example, you want to test a gear and you want to apply some angular velocity. So this is going to be the very right choice in your case, where you do not have any prime mover, or you want to virtually make any prime mover or a system where you want to represent this as a angular velocity source. So you have to take this block, add into your diagram, and just assign whatever angular velocity you want to give, and these values or these numbers will be converted into physical signals which are of actual angular velocity in the Simulink environment. So some blocks you are able to see as dark green, and let's say this one is some other green, and the remaining two are other green. If you see the bifurcation, their colors are different because they are going to be either angular or translation. So, or we can say the linear velocity or angular or rotational part. So all those rotational parts will be of this type of green color, and the remaining will be a little dark green, which represents the linear velocity, or we can say translation velocity. Now the same holds true for the electrical blocks. What you see here are the electrical blocks, and all these electrical blocks are actually represented by the blue colors. So whatever here you see are all blue colors. So Simscape has assigned blue color for electrical elements. Now something you will see over here is a rotational electromechanical converter, which is combination of electrical and mechanical system. So for example, the solenoid which we have seen earlier. So here you will have something with the red color as well, right? So in Simscape, the colors represents some different types of signal. So ideally for Simscape toolbox or Simscape block set, we have blue color for electrical and green for mechanical. And here you have everything for gas, hydraulic, magnetic, and maybe any physical systems where they are periodic operators or they are thermal elements. So here you have the thermal represented as the red one. So here whatever you see, all these are thermal elements, as you can see in the highlighted block, and they represent the red color. So red is for thermal. So whenever you open any diagram and you see some different types of colors, so which means there are some color notations assigned to them. So let's go back to our untitled model and let's have a look at help file, and let's try to run a pre-built Matlab simulation. So what is a pre-built Matlab simulation? So when we click on the help, we have to go to the main window for finding the help button. So on the Matlab main window, so this is a main window where you have a command window, a workspace, and your current folder. So from that you will get the help. So from help, when you click on the help, and let's say you want to explore the Simulink and you are just interested in let's say some kind of a mechanical system which is a pump. So if we are interested in pump, when you type just pump over here, so this is a search toolbar, and whatever you type, all those results will come. Now the results may be of different type. So results may be the function, results may be the blocks, results may be some examples which are highlighted by this bulb. So wherever you find this bulb, they are actually the examples. So here we have few example: well with jet pump, or hydraulic motor driven by load sensing pump, right? So let's open any of the example and let's try to understand what this represent. So, and actually you have lot many examples which are built in by the Simulink itself, and here you can see a path where these examples are located at. So these examples are in your Matlab installation directory, the example folder, then the Simscape fluids, then you have other subcategory of the folders. So you have this many different types of example. Ideally, the Matlab has created for better understanding and the better usage. Each and every block or each and every element is associated with some or other type of an example which is built in. So let's open up this built-in example. So when we click on this, it's going to show us the help file for this and whatever is the system under consideration. So I'm not going to discuss the technical part of what's happening in this example, but let's focus on how we can get all these results, right? So we are interested in finding out what is all this model about and how we can actually run this built-in model. So once you have clicked on the well with jet pump, there is a key over here where you can open the model, right? So I recommend you to first read out whatever example you are going to try out. Just read out the technical explanation and try to understand how the simulation is going to be performed and what are the parameters those are built in and what is the situation that is created exactly. So when you click on the open model, and a model will open in another window. So this window will consist of this type of pump, and when we click on run, this is going to be a ready to run model, right? So it's possible that you can create your own model, but you can also view and run the built-in demo models, right? So this demo model is included with some green part, which is a velocity source. And if you remember, just we have seen this ideal angular velocity source, right? So this is going to provide an ideal source of velocity. And what is the velocity which we are giving? This is a constant number, and this constant amount of velocity, which is again converted into from RPM to radian per second from this equation, that is given to this velocity source, and that is given to a centrifugal pump. So the centrifugal pump is going to actually run some of the mechanical system where you have some tank over here, and there is a pipe, 1, 2 and 3 pipe, and here you have a jet pump, and there are water properties also assigned over here, and here you have another pipe. So once you run this simulation, you can observe the results over here in this scope window, right? So what are the all things which are plotted? They are Q2, Q1 and QT. So Q2 and QT, they are going to be plotted together in the same graph, and there will be another graph for Q1. So if I hit on the run, I need not to configure anything, or I need not to change anything, just to get the same result which is discussed in the help file. So right now our model is getting compiled, and if you have any errors, if you get any sort of parameters you have changed, it will not allow you to run unless and until your model is error free. So that is called the compilation. So compilation is nothing but checking for errors. So here your results are available, and whatever are the values from 0 to 10 seconds in this result, they are plotted in the scope. So what are the Q values? Here you can see. So this is the flow rate represented as Q, and they are this is going to be the flow rate primary, and this flow rate secondary, and the flow rate of the tank. So these are the flow rates which are plotted, and here you can see from 0 to 10 seconds, for which was our stop time of the simulation, these results are plotted. Now if you give some different angular velocity, instead of an 1800 RPM, if you give some 1000 RPM and remaining parameters are all same, you will get maybe a different flow rate, right? And if you may change the pump related configuration, or maybe the tank related configuration, or pipe and the valve related configuration, then all those change configurations will result into the changed output. So here are the results, and here there is one more feature of the Simulink, that you can run your simulation from the results window itself, right? So this is going to be the case where you press the green button, which is again same as this green button, and you can run from either of this window, and the simulation results will be plotted here. Now when you see this, you will actually realize that this model is having some text information as well, right? So let me zoom into this model. How you can zoom in? It's very simple. You can just scroll down or scroll up, or you just use the scroll button to get zoom in and zoom out. So what you see here is the help file, or we can say some standard Simulink template file, right? So here you will have plot flow rate through the jet pump. You can also explore the simulation result using Simscape Result Explorer, and you can also learn more about this example, which is nothing but the same file which is we referred as a help file, which is this help file. So which will open up this one. So here we have the help related things well documented, and if you remember, all these things are related to the templates, right? So when you create your models using template, this block or this minimum things will be there in your model file. So I hope you now get the idea about how to run a demo. So running a demo will actually help you to learn yourself about how we can do the simulation and how to visualize the results. Now few more things about result. Let me explain you some results in a very brief. So what you see here is the result configurations, right? So whatever you have here are the main buttons in which you can see the result. So in the first plot here we have a 2 graph. So this 2 graph, as I am highlighting here, are nothing but flow rate secondary and the flow rate of the tank. So let's see what is the difference between these two. What is the difference between the flow rate of that secondary and the tank? So if I want to zoom in, I am required to use this part, and this is going to be the zoom option. So let me use the zoom option, which is horizontal zoom, vertical zoom, which is called zoom X and zoom Y, or we can use a simple zoom in by selecting this plot, right? So I'm making a square part, and I just want to understand what is happening in this duration of time. So now I see almost yellow and pink line to be exactly overlapping each other. So let's understand, are they exactly overlapping, or are there any other difference as well? So if we want to do that, we can do that by using the zoom, which is zoom on one axis and zoom on other axis as well. So I think if we zoom on a little bit, where we have now the second or now the time axis, which is very near, right? If you see this time difference or time represented by 1 unit, which is 1.776832 second and 1.776832 seconds. So this is going to be a very little time, and there is almost no difference, right? So they are exactly overlapping each other, and you can say the value of the primary flow rate is around 104.7, right? So this is about how to visualize the results, and there are other possibilities as well where you can use the markers, and if you click on this, the cursor measurement will appear. So what is a cursor measurement? So the cursor measurement window will appear on the right side, and it will give us the idea about what is happening. So if you are able to read what is happening? See, there are two cursor. One is the first one, or one is a I will say the scale number 1 or the point number 1 of interest, and other is point number 2 of interest. So what is happening between point 1 and point 2, that is explained here. So what is the time change? And it is approximately 1.77 second, and these values are also nearly same with the yellow trace selected, right? And whatever you see is a delta, and whatever you see is a time change and a value change. So how much is the value changing for this yellow? That is 196.425 GPM per KS. So that's something with per 1000 of seconds, right? So this is about how you can use the trace, how you can use the cursor. Now if I deselect this, and it's up to me that to what point we need to use the cursors, right? And at any point of time you want to go back to the fundamental view where you have all the 0 to 10 second. What you have to do is use this part or use this button to just select how you can come back to the main picture, right? So here is how we have come to the main picture, and I need to deselect the zoom. Right now if you see, I have already selected the zoom, and the zoom part is showing me the dark. I need to just deselect it, so now it's not dark, and now I can move my cursor 1 and 2. So can you observe the changes in cursor 1 and 2, and whatever is the delta t and whatever is the delta y, right? So let's say in delta t is 5.4 seconds. So in the 5.4 seconds you have a delta y change of around 1. So this is what you can use the cursor and what is happening at a different time. Now there are configuration parameters as well, right? So let me remove the cursor first. So if I want to remove the cursor, I need to press this again so that the cursors will remove. So now the cursors are not present, and now I'm going to start with the configuration properties, which is this part. So in the configuration property here, in this window you can see the number of input ports. So here are the number of input ports. You can give a simple time as well here, and there are some other parameters, and you can actually choose the layout of the plot as well, right? So here you can decide how is going to be the layout. So this is a layout option, and where you can choose the multiple things: time span, the display, the limits, and whether you want a data logging or not, and what if you want to log the data to the workspace, which we'll see later, you can make it enable from here. Now a very fundamental thing to be done is let's say here the values are from 104 to 105 for primary flow rate, right? So you should not get it from 0 to let's say 500. So if you get a plot from y values from 0 to 500, it's not going to make sense, right? So all those scales are going to be selected by default. If not, you can change it from here. You can change it from all those axis scaling from here, and what is going to be the axis values from here as well, right? So you can adjust the minimum and maximum y limits, and your time limit can be again changed from here, which will also affect the similar time changes. So this is about the configuration properties, and most of the time if you do the auto scale, it is going to be get adjusted properly. And if you want to get display, you can click on the show legend, right? So if I remove this, it was already there, right? So if I remove this and OK, I'm not going to get what are the signals, what is represented by this yellow line and pink line. So for that, again, I'm going to click on the configuration time, display and show legend. So if I select the show legend here, the show legend part is going to give me some idea about what are the signals. So if I enable this and press OK, now we have the legend of the plot. What is the actual signal that will be given. So with this, you have the basic understanding of the visualization or how to see the results, and probably there are so many other options where you can select about taking a snapshot. Maybe you can freeze the screen. You can actually whatever are all these options, they are listed here as well, and you can actually make copy to clipboard as well, right? So once it is copy to clipboard, you can easily paste it anywhere, and you can take a print of this file as well, right? So if we do the copy to clipboard, right, now it's copied in the clipboard, and if I just want to paste it in a paint, so this is going to be the output case, right? So if I just now press Ctrl V, we are going to get the plot like this, right? So copy to clipboard option is a better option when you are representing or when you are showing the result as a part of the report. So maybe if you can choose a print where it is going to be exactly the black background, but normally for a proper technical documentation, it's always recommended that you avoid the black background, and for this it's going to be the better option where you have copy to clipboard. Now when you copy to clipboard, the legends and everything will also be included here, right? So this is going to be the result post processing, or maybe the technical reporting part of it. So coming back to the results, let me close this window. Now let's say for example you updated something with the velocity source. Instead of an 1800 rpm, you change it to some other value and you will have some other results. So in order to remember or compare with the previous results, you may use the copy to clipboard button. So this is about how you can open up the help file, and you will not be able to actually make any changes to the default files, because they will be again affected, and so that you will not be able to reproduce the very results which are there or which files are generated by the MATLAB engineers. So coming back to the help or documentation part is very strong, and here you can see many different things related to, let's say instead of an example, we want to have some help related to this part, right? So variable displacement pump. So we want to know how MATLAB can help us modeling this. So if I click on this, it's going to show me that what is the block available with the MATLAB, right? So if I show you, this is going to be the library, and pumps and motor, we already have a typical block which will look like this, and it is nothing but a variable displacement pump. Now how does the variable displacement pump works? It's all related curves, P and T and other related diagrams, they are available over here. With this window, you can actually press the control and scroll up, and you will be able to see the help with a bigger font. So what is this block about? What does this block help you to model? What are the conditions taken care of? What are the equations implemented? And what are other related things? So are there any saturation effect? Are there any leakage flow rate considerations? And everything about that model. So if you want to understand what are the inputs, what are the outputs, which are the ports, what are the parameters you have to configure, everything is listed over here. Now another important part, if you want to use some of the related parameters, right, or let's say you are interested in something else which is nearly similar to this, then you have see also part, right? So when you click on the see also, you will be able to understand what are the other options related to this. So you have a fixed displacement pump TL, variable displacement motor available, and it is going to be look like this, and it is also similar in a way, right? So this is about the help. Now how to scroll through or how to browse through the help is also very important. What you see over here in the top left corner is how you can go through the help, and if I click on the back button like this, I am going to go to the previous page which I explored. So let me go back again, and here we are back at the pump page. So these are the results. So the results of the pump, and there are so many other things where you have an example along with the help topics, analyze and select the features of pump diagnostic, and you have a closed loop actuator, and where you can see there are actually many results coming up, right? So there are total 252 search results within the Matlab related to keyword pump. So I think you will be now more clear about what kind of help or what kind of label Simulink offers in order to do a simulation with a pump. So let's go back to this, and here you are back at your main Simulink page, and what you see here is Simulink toolboxes. Again, they are in the alphabetical order. So whatever are the toolboxes related to that, you can get the idea, right? So here, let's say if we want to go to Simscape electrical. So in the Simscape electrical, you can start through the applications, maybe electrical block and the control and specialized power systems as well. So if we go back and browse through all these toolboxes, and let's say we have a Simscape, and in the Simscape also you have physical modeling, and how the physical modeling is taken care of. And here you will be able to see the mechanical models, right? Here you will be able to see the hydraulic, thermal models, and other related models. So if you click on the mechanical models, you will be having again a classification. Now this is same as if you are browsing your folder in your Windows environment. So you will see all the folders similarly situated like this, right? So let's say we go to the rotational elements, and we have all these things, which is let's say we are interested in rotational damper. Then if you click on the rotational damper, it is going to open up that library block. So this is going to be how a rotational damper will look like. And if you see the theory, what is the equation behind the damper and how it is implemented, that is given over here. So this is about the damper. And if we go back, and let's say if you take a rotational spring, you have something related to spring, and maybe you have some other blocks as well. So let's go back and let's understand some of the mechanical systems related help. So here we have a mechanical system, and what you see as all the block is they are simple mechanical systems, the linkage system with a translation frictional mechanical system with a translational hard stop, and many other featured examples. So here are the featured examples which are going to use all those blocks which are dark green, which are going to have a linear motion, and the another color of green which is light green, and you will see the rotational motion. And I think now it's a good time for you to open some of the model and try to understand how the Matlab is going to simulate it. Now coming back to the Matlab, here let's say this is the first file which we have created, and I can open up this file. And so this model was 12.3T, right? And where T is represented by this ramp input, and this is our commented out block, right? So we ran this situation and 12.3 multiplied with the 10 at the end of the simulation, which will give us the display of 12.3, and what we'll get in the scope is going to be the continuous increasing value starting from 12.3 to 10 times of that. So this is our first model which we created, and now you can undergo the very fundamental exercises where you implement your own equations and test them in the Simulink environment. Thank you. Hi students, welcome to part 2. In this section we are going to learn about simulation configuration and Simscape. So we'll first understand why it's very much important to understand about how we configure our simulation. And by configuration we mean that what are the parameters we are going to assign and how we are going to run the simulation in such a way that this configuration or this settings of the model represents the real world scenario, or we can make it more realistic. So let's learn about the simulation configuration. Before we start, let's understand what are the Simulink toolboxes, and sometimes they are also known as Simulink block set. So a block set or toolbox is nothing but a group of similar models put together. For example, if they are electrical elements like resistor, capacitor and inductor, they are put under one toolbox, and let's name it as electrical toolbox. And there are some fundamental hydraulics related stuff, there are fundamental other stuff which will be categorized as either toolbox or block set. Now this toolbox and block set are actually based on the applications. So whenever we discuss about modeling of any engineering system, we are going to discuss with specific application. So according to the type of application, the Simulink toolboxes are like this. So there are signal processing related toolboxes, and they are purely related to audio and digital signal processing. And there are certain image processing and computer vision toolboxes. There are control system toolboxes as well. And here you have a model predictive control system. Here you have a Simulink control design and design optimization as well. Now with the Simulink you can actually make a data acquisition system as well. Instrument control toolbox is also added. Another communication category is antenna and radio frequency wireless toolbox, which is nothing but a Wi-Fi or wireless LAN and 5G. And there are autonomous systems as well, where you see the automated driving toolboxes, where you see the sensor fusion and tracking toolboxes. And here you have some toolboxes related to the hardware stuff, which is called hardware description language coder or HDL verifier or system on chip block set. Now in the automotive application, these are the toolboxes which are added. So this is automotive, this is aerospace, and here you have something for system engineering. So these toolboxes are important when we learn about basic electrical and mechanical system modeling. So here you have a vehicle dynamics block set. Here you have powertrain block set as well. And in this case, if you want to implement any logic, which we are going to learn in this course as well, which is a Stateflow. So these are the important Simulink toolboxes and block set categorized according to the application. You can visit the MathsWork website in order to again look at the another category where you have different toolboxes in a classification. So where you see the fundamental blocks are actually going to be the part of very basic blocks, right? And then you will have a system level block diagrams. So this is also important. A system level engineering is also done using the Simulink. So with this introduction, let's start with the simulation configuration. So why simulation configuration has to be right? So what will happen if the simulation configuration is wrong, right? And what are the important parameters? Someone is interested in how does the engine starts. Some person is interested in knowing that what are the dynamics involved in starting of an engine, right? And the starting dynamics of an engine can be related to a starter motor, maybe some gearbox, and maybe some solenoid, or let's say some relay or contactor type of an arrangement, or ignition, and maybe the battery, and along with the engine with its control system. So engine along with the control system and all these parameters put together are going to end up starting an engine, and which may be taking, let's say, around 5 seconds. So this is our interest, where how does an engine start and how effectively all these components are playing their role. Now on the other hand, someone is actually interested to figure out what is the overall engine efficiency, right? So these are the two different purposes, where we have a similar system where engine and its control both are present in all these two cases, but we want to understand, or we want to study different aspect of the system. So here it's only starting, here it's overall efficiency. So overall efficiency is going to involve, let's say, the fuel type, the fuel energy content, and again the engine along with its control. So engine along with its control, how you are going to run the vehicle, right? Or how the engine is run according to its speed and torque demand. So this is going to be the case in overall efficiency. And what do you think, for how much duration we should run the simulation which is related to engine efficiency? Any guess on the timeline? Yes, it has to be definitely far greater than the 5 seconds, which is just time required for an engine to start. So the overall engine efficiency may be, let's say, 5 minutes. So we want to run an engine for 5 minutes, and within this 5 minutes we want to take the idea about what is the engine efficiency with reference to different speed and torque, and with reference to different control systems. So these two simulation configurations where the engine and control blocks are common, but their time are different and their purpose are also different. So therefore the simulation configuration is very, very important. So first you need to identify what is the purpose, and accordingly you select a timeline, and whether you are interested in the transients or dynamic, that is going to decide the overall system. So simulation configuration parameters will decide what situation is of our interest. So whether we are interested in transient, which is a kind of start of an engine, or whether we are interested in efficiency of a system, where let's say the engine is going to run at a constant speed, or we are interested in overall efficiency, or let's take the average of all number of efficiency at each point. So the simulation purposes may be different, and all the configuration parameters are very, very important. And in order to configure your simulation or your model to match with this, we need to understand very fundamental concept. So what are these fundamental concepts? So these are important simulation terminologies. So I'm going to introduce now the very fundamental terminologies for simulation. The very first thing is simulation time, and you must have observed this simulation time is nothing but actually the stop time in our case. So the stop time is nothing but what we have seen in the Simulink window, and for how much duration you want to run your simulation. So that is called a simulation time, and this is the first important parameter for configuration. The second is run time. So if you have observed, the simulation stop time we have kept it as 10 seconds, right? And did the simulation has taken actually 10 seconds? No, it was quite faster, right? Because the model was quite simple and it was 10 seconds is not going to be a large amount of time. Now, let's say, for example, if you run your simulation for 1000 seconds. Now, is it going to take actually 1000 seconds in your computer? No. So runtime is nothing but the amount of actual time taken by a model to run in any computer, right? So that depends on your PC or maybe any computational device on which you are running your Matlab, and the speed of that device along with certain other configuration parameter which we are going to study. So the runtime is another important parameter which represents how much actual time is taken by the computer to solve the model or to run the model. So this is the second important terminology, runtime. Now you are very clear about what is simulation time. Let's say the simulation stop time is in 10 seconds and the actual time for the corresponding 10 seconds may be a less than a second, right? So if your computer is fast and if your model is simple enough and your configuration parameter or your sampling time is different or let's say sufficiently high, then your stop time will be somewhat around 1 second, and this is not going to include the compilation time and other settings as well. So let's go to the next step or the next terminology, which is a sample time or time step. This is very important terminology. A sample time or time step is nothing but the time duration, or let's say a piece of time for which the model is solved on each time step. So it sample time, a time step which represents the duration after which your model is solved again, right? So the model is solved frequently with the varying inputs or with the varying conditions. So after how much time your model is going to be solved again, that is called a time step. So let's say you have a total simulation time of 10 seconds, and for 10 second simulation time your step time, whatever you have configured, is 0.1 second. Now every 0.1 second in the simulation your model is going to be solved, all those equations are going to be solved again. So within 0.1 second your model is going to be solved one time. So how much is the time you are allowing your simulator to solve all the equations of your model, that is going to determine the sampling time or time step. So we are going to see this very important parameter, what is going to be the time step, right? So let's understand another important terminology which is called a parameter sweep. So let's say, for example, we want to simulate the Ohm's law for a resistor. So Ohm's law tells that whatever is the voltage across the device, that is proportional to the current passing through it, provided there is no change in the temperature. So voltage is proportional to current, and that constant of proportionality is nothing but the value of the resistance R ohms and multiplied with the I. So that is a voltage equals to R times I. R is a resistance value in ohms. Now in this case you want to analyze what will happen if the temperature is changed. So you can have an equation of resistance at a given temperature, let's say R at T. Now R at T may be a different characteristic. Let's say it's going to be like this, or maybe for different type of material, whatever is the temperature and whatever is the value of the resistance, that may be different. So if the temperature is going to increase, the value may decrease, right? So that may be the negative temperature coefficient devices. Now in short, you want to actually understand the effect of temperature on the resistor. That can be carried out by parameter sweep where you run your simulation, let's say for 100 number of seconds, and in the 100 number of seconds your temperature is, let's say, 20 degrees centigrade for first 20 seconds. Then your temperature has been increased to 25 degrees centigrade for next 20 seconds, and you keep on increasing your temperature every 20 seconds. Let's say the next temperature is 35 and another is 45, and due to this all change in the temperature degree centigrades, what is going to be the effect on the current passing through it and the voltage across this device? So that can be understood by a parameter sweep. So these are 4 important simulation terminologies. We will learn how it can be built. We are going to learn about how this parameter sweep can be taken care into the simulation. Basically what we are going to do here is, how do we change a parameter? How do we actually change a parameter which is not fixed and while the simulation is running, and that is called a parameter sweep. So how do we change a parameter during runtime and which is not declared previously, right? So this is going to be very important when we are going to learn about real world situations and try to model the effect of change in the parameter when the simulation is actually running. So now we are going to explore the time step a bit in detail and understand about its pros and cons. So before we understand about the actual time step and what are the options for configuration of a time step, we will learn about how does a simulator work. So a simulator is going to first compile, as I discussed earlier. So the first step is going to be the compilation. It is going to be exactly the same way where your text code, or let's say your programming language, is compiled and it is going to be translated into some other language. So the translation is nothing but the compilation. So the blocks are translated into executable code, or they are nothing but the equations, right? So a simulator, before running, it is going to compile your block or compile your model where all the blocks are present. Now after this, once it is translated in the backend, equations are computed. So basically the Matlab and Simulink is a technical computing tool where all the equations are computed at each time step and signals and states are updated. So what a simulator is going to do is, all these equations which are translated, those equations are computed at each time step, right? So every time step, this values or these equations are calculated again, and signals and states which are related to this model, they are updated. They are going to affect it, or they are going to change according to whatever are the equations fed into. So what is the meaning of a backend? So backend is something which is you are not able to see. So if you have your own programming language or a script file.m file, you will be able to see what's happening because you have written the code. Now blocks are translated into the equivalent executable code, which is not going to be involving you, right? So it is going to happen in the backend where the user or you as a modeling engineer will not know how it is translated and what has happened, right? So the backend is going to be the all equation solutions, right? But it is also important to learn what is going to happen in the backend, right? So even though, because you are not kind of a programmer, or you are not going to kind of your own program to execute another program, but you will be able to understand what happens in a backend. So it's similar to solve the equations by placing the increasing values of time instance, right? So how does a simulator work? So let's say you have an equation. For example, we have created our first file where it is 12.3t, And in this 12.3t, let's say the output y equals to 12.3t. How does a simulator work? So simulator is going to put all different values of time and calculate all different y's and plot the y. If your y or the output variable is any other complex combination, it may be an algebraic equation or a differential equation, or maybe any other complex model which is going to be solved in the backend. So all the equations are going to be solved. What is the important keyword here is a solving, right? So solving the equation is going to be the task which is happening in the backend. So how does this solving occur, right? So the Matlab has various different types of solvers, and there are types of computations which are performed while simulation is running. So for example, if we take an equation where 2 plus 3e raised to t, and you want to compute this value of function, let's say your y is output and y of t is going to be like 2 plus 3e raised to t. So here you have a 2 default value, and now you have an exponential added to this 2, and you keep on putting all different t values, and you get nothing but a graph. So a simulator exactly makes a graph of a function. Now this function may be as simple as this, or maybe very complex as pump, where you have multiple equations acting together. This is going to be the working of a simulator in a background, or in the front end, whatever you are going to see is nothing but a GUI, or a graphical user interface. So what is the difference between a continuous and discrete system? A continuous system is where the time is considered as continuous, and in discrete, where we consider the time is not continuous and there is some time gap, or there is some time difference between two time steps. Obviously, it's not possible to run any model on a purely continuous basis, but we can analyze that with a sufficient high value of sampling time, which is denoted as, let's say, TS as a sampling time. If you have a sufficient high value of sampling time, and your observation of understanding the system, or your observation of this time, is going to be a larger dimension, then you can assume that it is as equal as a purely continuous system. So this is the very fundamental difference. How do you run your blocks in the background, whether your system is going to have a continuous system or a discrete system. So let me give you an analogy or an example of a continuous system and a discrete system. So what you see here in this GIF file or an animation file is basically the needle rotating without any delay, right? So probably you and me are not able to capture any delay happening with this needle movement, and therefore we see the time to be continuous. Now at the same time, if you see a clock tick with a normal clock, which is going to be like this, and this is an example of a discrete system. So discrete system, you will have actually delay in two time step. So here you do not have any delay which is observable, but actually it is there. Here you have a delay which is quite sufficient so that you can observe as well. So this is a very fundamental difference between continuous and discrete system. So let's now understand what are the Simulink solvers. So here there is a library of solvers, and according to whatever is your model type, your solvers will be decided. So let's understand what is the hierarchy that is followed in choosing the solvers for your simulation. So here is a flowchart or a graph which will help you to understand what are the types of solvers. So do you have a fixed step solver? Then yes. And is your model having continuous states, or is your model having discrete states, right? So then you have a fixed step discrete solver, and if yes, in case of a continuous states, then it is going to be fixed step continuous solver. If it is not going to be a fixed step solver, then it is called a variable step condition over here. Now let me explain you what is the meaning of fixed step and the variable step. If during your simulation, if your step time remains same, right? Let's say you have a total simulation time of 10 seconds, and in that 10 seconds your step time is going to remain fixed as 0.01, let's say for example, and it does not vary throughout all this 10 seconds, then it is called a fixed step condition. Now sometimes you may require to have a variable time step, because during transient you want to have your step time to be very low, and during steady state you may require your step time to be very high, so that your overall runtime is going to be sufficient so that you can run your simulation quickly, right? So in that case the variable solvers are required. So the variable step solvers will inherently change the step time. Now who is going to change the step time? So the Matlab itself, or in the backend, it is going to take care of what is going to be the step time. So now the step time is not fixed, it's going to vary according to your configurations and the way Matlab treats the model. Here also you have another two categories, which is variable step discrete solver and variable step continuous solver. And here you have a fixed step continuous solver and variable step continuous solvers. They are classified as different names, and these names are nothing but ODE, which stands for ordinary differential equation of first order, second order, third, fourth, and so on, right? Here you have a variable step continuous solver, ordinary differential equation solver of 15th order, maybe 23 order, and the S and T stands for stiff or non-stiff. So these are Simulink solvers. Sometimes actually you need not to worry about what is going to be the solver, because you can choose the auto both in terms of choosing a solver as well as the step time. So when you make auto, the Simulink in the background is going to take care of what type of simulator or what type of model you have, what type of blocks you have, and it will be adjusted automatically without compromising the accuracy of the model. So how does an auto solver work, right? So the auto solver is going to decide whether it's fixed type or variable step type, right? Now if your system has only discrete states, then it is going to be fixed step discrete or variable step discrete. Now if your system is going to have the continuous states as well, then it will be either of these four category depending on the fixed step or variable step. And based on the automatic solver configuration, if you have a fixed step configuration and you have a continuous state with ordinary differential equation, then it is going to be ODE3. If it is going to be a differential algebraic equation, which is DAE, then your solver is going to be ODE14X. So whether your model is stiff or non-stiff, that is another different category. The auto solver is going to assign this type of equation solver. Now what is basically a solver? A solver is nothing but a software, or we can say a code written in order to solve your equations, right? So a solver is nothing but a program, or we can say a software or a code which is written by the Matlab engineers, where your model is going to be solved based on this program, right? So if you have heard of basic differential equation solvers and the methods, which is a Runge-Kutta method or maybe Euler's method, these are nothing but the mathematical techniques or the numerical analysis which is going in the backend. So this is about auto solver. Now what are the Simulink data categories? Now how does the Simulink treat the data, right? So these categories are very important. The first category is a signal. Signals are nothing but the block inputs and outputs computed during the simulation. So this is one category, and signals which are nothing but inputs and outputs, and they are computed during the simulation. They are going to change, right? So it's possible for you to change the inputs as well, and outputs will be also changed accordingly. Another data category is states. Now states are nothing but the internal values representing the dynamics of the block, and they are also computed during the simulation. So they are not the final outputs, not the predefined inputs. They are nothing but the internal states or transition values from one point of time to another point of time. The other category is nothing but the parameters. Now parameters is nothing but the values that affect the behavior of a block, and it is controlled by the user, right? So the user has to give some input parameters. So for example, let's understand what is the meaning of all these things, right? So let's say we have taken a block in the Simulink which represents an engine, and there are some multiple inputs and there are some multiple outputs, right? So all these are called signals. So the input things are called signals, and again outputs are also signals. Now whatever is happening to the engine inside because of this input signals, they are called the states. So states are nothing but the values of signals at each point in the engine block, right? So if you explore the engine, what is inside the engine block, you will have all multiple different types of blocks, and all those signals at multiple types of blocks represents the internal state. Now what are the parameters? So the parameters are nothing but how you assign the values and which does not get affected during the simulation. So parameters are nothing but, let's say, the horsepower of an engine, or let's say the value of the maximum speed of an engine, right? So maximum speed, the horsepower, maybe the torque, and any other parameters which are fixed or which does not change while the simulation is running, they are called as parameters. So we need to differentiate between all these three very clearly. Basically what Simulink is going to do, Simulink is basically going to compute the new values from the signals which are given as inputs and the present states, and it is going to create all new variables. So if you specify the parameters when you are going to build the model and can occasionally change them while the simulation is running. So it's also possible to change your parameters while the simulation is running, and which is exactly the same thing we discuss as parameter sweep. So it's also possible, but it's not always, it's going to be occasionally. So what are the Simulink model options, right? So sometimes we are discussing about the engines, right, which is a very complex system. Sometimes we are discussing about RLC parameters related to electrical, or spring, mass and damper related parameters, which are basic building blocks of mechanical systems. So what are the options? So is it possible both the ways? So yes, the answer is yes, you can do both, right? So the Simulink model options are possible where you have a very complex system readily available, as well as you have a very fundamental block so that you create your own engine model as well. So it's possible in both the ways. The first thing is the fundamental block, which are nothing but spring, mass and damper, or maybe RL and C in electrical engineering case, and other is the ready-made system block. So the ready-made system block is nothing but the engine, or you can have a gearbox or something like that. So this is going to be like a Lego block, right? So where you have the fundamental blocks are Lego blocks, and it's up to you what kind of system you want to make. And now you can actually create your system, and you may have a multiple number of subsystems as well. And the ready-made blocks are nothing but like this, where you have part or a system which is ready, which will look like something this, or which will behave in a certain way, right? So these are readily available blocks, and you can pick them and place in your model, or you have also an option that you create your own model. So initially, as a beginner, we are going to go ahead with the readily available blocks, right? So that our task is going to be easy in order to run a simulation. Now, let me give you some introduction to the Simscape. So Simscape is something where it's readily available library. What you see here is an equation of the acceleration, velocity and the displacement, and these are nothing but the integrator 1 over s. They are called the integrator, and m is the mass, this is a b is a damping coefficient, and k is a stiffness coefficient of the spring, and this is how you get the value of the x. Now the same system in Simulink will look like this as a block diagram, and in Simscape you can take up the mass block, damper block and spring block readily available and apply some force to this model. So this is going to be a very simple thing, right? So Simscape is going to be actually related to the physical simulation. So all physical simulations are now part of the Simscape library. So Simscape library is recently built by the MathWorks, and it is nothing but all physical signal simulations, or it is actually covering everything: electrical, mechanical, electromagnetics, maybe thermal and fluid and so on, right? So Simscape is actually covering all physical simulations. So now it's the time to start our simulation and understand how does a system model works, or how we can step by step create the model. So we are going to take an example of a lever mechanism. What is a lever mechanism? So fundamentally, a lever mechanism is going to have some kind of an arrangement, or let's say this is a metal rod and it is going to be fixed at this point, right? So let's say a metal rod is having length A, B, which is a total length, and C is going to be a point from where it is fixed to a point, right? Or where it can move. When you apply some force in the downward direction from this A is going to go upward, right? So this is a basic lever, or called a linkage mechanism, and let's actually build a lever mechanism simulation in the Simulink. So for more clarity about the lever mechanism, if I shift this C point to the middle, right, or where exactly the case is AC equals to CB, if both the lengths are equal, then it's going to be a typical case of a seesaw, right? So this is going to be the typical case where it's a seesaw, and this is point A over here, B over here, and AC and BC, both the distances are going to be same, and C is going to be the fixed point, right? So whatever is a force applied, that will be translated to the point B, and this is going to be a very simple lever mechanism. So let's explore Simulink for lever mechanism. So now let's start with creating a model for a lever mechanism. So in order to start with, we'll first create a blank Matlab model, and let's first of all save it in a folder where we created our first file. And remember to name them as actual file, which is going to represent something, and its name represents what exactly it is, right? So maybe this is your first lever experiment, or let's say your first lever model file. I'm going to name it as lever 1. So I've saved it as lever1.slx file, and this can be accessible in the same folder, which is our current directory. Now I want to start with a lever mechanism. So instead of going into the Simulink library file and searching here for a lever, we can directly search the same in our untitled model itself. So I'm going to search here as lever, and here is a foundation library of mechanical and mechanisms. So here we have a lever available, and what you can see with the lever is actually the 3 points A, B and C. Now, how do we start modeling with this, right? So, or what exactly we want to do? Let's say we want to apply some force to A point and get the output on the B by keeping the C point as a fixture or as a reference. So in order to do this, first we have set our basic objectives, what we want to do with this. Now it's a time to double click on this lever and open up the help file. So when you double click on the block parameters, this window will open and it will explain you lever mechanism in its generic form, and it's known as a free or summing lever, and it has 3 lever pins, and this is how it is going to affect. Now what you can input, what you can predefine for this lever as a physical model is the length of AC arm and the length of BC arm. So the AC and the BC arm you can fix, and their length can be in the meters. So let's keep it as 0.1 by default. Now if you see here, you can actually open up the source code and see how the lever looks like. So this is how the lever diagram, or let's say a lever as a block, is converted into .ssc file. So let me give you an idea. So this is an Matlab editor, and here you can see the lever.ssc file, which is nothing but a Simscape code file. So Simscape code is a different language than the Matlab M script. It's slightly different, but it will give you the idea about what exactly it is. So if you are not able to see it properly in the screen, let me go to the configuration and let me help you to how to configure the font size. So for configuring the font size, which is here, you have to click on the preferences. So when you click on the preferences, it will give you the option to change the font size. So in this case, what you see here is a font available as in the middle line. So when I click on the font, you can change the font, but I'm basically interested in changing the size of the font from 10 to, let's say, 24. So this is going to be the demo, and if you click on OK, now you will be able to see it properly. Now you have changed your system font, and you might have done with the same procedure in your scripting exercises. So what you see is there are 3 nodes created, A, B and C, and all the basic values which are given in the model, they are now available here, and the parameters are specified over here. So here you have the variables which are forces at A, B and C, and this is basically the calculation which is related to all the parameters. So this is how simply your lever is converted into an equivalent Simscape code. This is just for your information, and likewise in the background, all this whatever is affiliated with this block, that will come here, and the Matlab solvers are going to execute this program. So let's come back to the model environment again, and here we have the lever block, and we want to assign some values. Let's say we keep the values same, and now we have seen the source code. Now let's click on the help over here. So you can see the help menu of each block, which is located in the box in the bottom side of the block parameter. So if we click on the help, the Matlab documentation related to lever is going to come up, and whatever you see, that theory associated with the lever, that will be reflected over here, right? So whatever are the forces, whatever is the LAC, LBC, which are the lengths, and FA, FB and FC, all these calculations or the fundamental theories are explained over here, right? So if you fix the point A or maybe any other point, whatever are the cases with the forces acting, that is going to change, right? And how you need to assign the port, right? What is the meaning of A, B and C, and you can actually run a linkage mechanism help example as well. So let's now, after reading enough the technical information about how the Matlab has modeled the lever, let's start modeling itself. So now we have decided to apply some force at point A and to understand or to know whatever are the forces available at point B, keeping the point C as a reference. So now there are three things. One is I need to find a reference for C, I need to find some output, or we need to observe something at node B, and we need to apply some input at point A, right? So how do we carry out these things, right? So in order to do this, we have to search out for the source of the force, right? So I'm going to search SOURCE source, and which is going to be force, right? So I'm searching out force and source together, and here is what something I have got is ideal force source, and which is, here you have to read it, a foundation mechanism, right? So the foundation library and the mechanical sources, so this is going to be the right choice for our case. Now what is the right choice for your first model, that you have to decide, and you may require to actually figure out a couple of things on do some very fundamental exercise and study in order to choose the correct block for your case, right? So your case may be different than this, and how do you get help, right? So you need to search out for the various things, right? Let's say for point B, we want to find out something is related to force observation, right? So we want to observe the force. So if I write here observe the force, probably there is nothing like this, right? So observing the force is not directly available as a Simulink library block, and so we need to modify our search. It's not an observe. Let's put some technical word where it's a sensing, right? So if I type sense or a sensor, right, I'm going to get this block as a result. It's an ideal force sensor. So let's say we have now an ideal force sensor available, right? So, and if you want to remember, right, what this block is about, you can actually turn on displaying the name. So here is the case where you can actually show the block name, right? So if you select the middle parameter, then the block name will be shown. So I'm going to enable it for all these blocks, right, so that I can remember what is the meaning of this block, right? Because this block, if I'm seeing it at the first time, I may not remember what this is, right? Or for this block, I am not sure going to be this is a sensor, right? So if we click somewhere else, its name is gone, right? In order to keep the name, we can keep it as show block name from this menu option. So now we have the ideal force sensor, a lever, and a force source, right? Now again, we need to go into detail of what is what, right? So it's always better to read about those blocks before you run your simulation. So how to do that? So basically, if you read out this R and C, what is the meaning of R, C, and S? So port S is physical signal port, right, through which the control signal that drives your source is applied. So S stands for source. R is going to be the output of the force, where you apply the force, which is to be connected to A in our case, and C is nothing but the casing or a common reference, right? So if we do this, I need to probably rotate this. And how do I rotate this block? Because I need to connect the R with A, and it may not look properly, right? Let me learn how to rotate this block in such a way that it is going to be aligned properly. So you can right click and rotate and flip, and you can rotate it clockwise by Control R, which is a short key. So here is a rotate and flip option for you, where you can basically rotate any block. So I'm going to press now Control R, and okay, now probably it looks better. So here we have connected the R point to A point, and whatever is going to be the force value which we have to apply over here as input, right? So now we can apply some input which is going to be a number, or you can apply any other signal as well. C is going to be the common reference. Now let's connect a similar way what is going to be a sensor. Now in order to run this model, we need to understand how the sensor works, right? What is the input to the sensor and what is the output. So let's again learn from this help over here. So R and C are other ports, and connection F is a physical signal port that outputs the measurement result, right? So here R and C are going to be the similar case, the F is going to be the output, right? So I'm required to connect R with this part, right? Now C is going to be our common reference over here, and F is going to be the output in case of a number. Now with this basic exercise, let's create a common reference which is to be connected to the C point, right? So how do we find out the reference, or what is going to be the case? So here all these blocks are of same green color, and we can find out a reference which is linear motion reference, right? And if you search from a basic term reference, it is going to be so many different references, right? So probably you need to fine tune your search in order to find a correct block for you, and this is going to be an exercise which may take some time, and you need to invest your time initially to search out what are all the blocks, right? And this is going to be a reference, and let's say this reference is going to be some rotational part, right? So mechanical rotational reference. Now do we have any rotational references or do we have any rotational parts over here? No, I made a mistake, and I need to actually find linear motion references, right? So or instead of a linear, if I type linear, I'm not getting any result. Let me search for translation, right? So here comes the translation reference block. So this is going to be a mechanical translation reference block, and let me figure out, let me show the block name, and if I connect this, I need to connect now all these points, right? So C is one connection. Now how do I connect this C? I can right click over here and connect it, or maybe I can take up this arrow and connect to this part. So now here we have a C block, and now we need to connect this to another similar reference, and this is intuitive, right? Or where it appears automatically that where you want to connect. Now if you are making some wrong connection, let's say for example you are connecting this F block over here, right? Or you are trying to connect this F block over here, which may not be right. So let's see what happens, right? So your connections will appear always in red, right? So when your connections are firm, then only they will appear as perfect as green dot, right? So F is the output of the sensor, which we cannot connect to the reference, or it's not going to be a green signal. It's not, its signal type is going to be different. Remember here one thing, if its signal type is going to be green, then we could have connected it perfectly. So then logically it's not correct, but the Matlab will not show any error. So this is going to be the error which is generated by the modeler itself, or the person who is going to create the model, right? So if it is of green type same signal, we could have been able to connect to this place, right? But which may not work in our example, or which is going to be logically incorrect. So syntax wise incorrect are two things, or the model will not allow you to make any syntax error, and therefore it's going to be more clean, right? But you may have some different errors which you are not able to have visually available as this one. Now what we want is to give some input, and we want to visualize some output. And how do we do that? I think it's simple, and now you know some blocks which are, let's say we connect a display over here, and which is going to display the output force, and let's create some constant number over here, and which will give some input. Let's say this constant is value 10. So Now let me try to connect this constant to S part and display to the F part. So I'm going to connect this to this value, and okay, probably we are making some error. We are not able to connect it, right? See the red part over here, and this is a false connection. This is not connected at all. Now why we are not able to connect? Because this is going to be a Simscape library, and it is going to be a physical system, and this is going to be a number. So we need to convert this number into an equivalent signal. So how do we do it? So we need to convert this Simulink variables, or let's say a Simulink environment signals, into physical system. So what we need is Simulink to physical system converter, and that can be found by Simulink to PS converter, which is the very first choice coming up in the search result. So here we have a Simulink to PS converter, and I'm not going to have this block name displayed because it may occupy some space in my block diagram. So now I'm going to give this as input. Okay, now it's able to connect, and let me connect this to S. Now we are able to make another connection, right? So look at its difference in color. Here is a black, which represents the Simulink. Here is some other color, red, or it may be applied to green as well. So do you have any idea what we will require to connect this? Because this will also be not connected directly. So what is the type of block we have chosen here? It is Simulink to physical system converter. Now the display is also of Simulink type. So what we need is another converter, which is physical system to Simulink converter. Now in order to get that block, I can write like PS Simulink converter, right? So let's try to connect this and this one with this one. Okay, now it's going to be perfect. Now let's try and run this model for 10 seconds, and we are giving some input as 10, and AC and BC length are equal, right? So this is going to be a case with a seesaw. What we will observe in the output? What will be displayed at the end of 10 seconds here? Any guess? So here we are applying 10 constant value of force to the point A, and according to the AC and BC length, the forces will be calculated over here, and the B part is going to experience that much of deflection, or the B node is going to experience the change in its position, and that will be displayed over here, where C is the point of common reference, right? Now what will happen if I click on run? Are we able to run our model now? Let's try and understand. So if I run the simulation, here comes the diagnostic viewer, and it is suggesting something to us, right? Let's try to understand what is suggested by the diagnostic viewer. So this is a diagnostic viewer window, and if we have any errors, if we have any logical or syntax error, it is going to show up over here. So if you read out this diagnostic, what it is suggesting is this, right? So there is ideal force sensor, ideal source, then there is a lever, and each physical network must be connected to exactly one solver configuration block. There is no solver configuration block connected to physical network with following blocks, right? So this is an error, right? So the Simulink is asking for simulation configuration or solver configuration block. So how do we have the solver configuration block? So this block is missing in our case, and let me find out a solver configuration. So this solver configuration is going to be okay, so here comes the search result as solver configuration, and solver configuration is nothing but fx equals to 0. What is the meaning of fx equals to 0? This is going to form an equation, right? So when we have such a system where we have some Simscape code running in the background for this model, and this, we need to apply some common reference or common solver, right? And we can connect this solver reference to this part, right? And you see that if we connect like this, it's not going to be correct. it's going to be correct, then it will appear as a green dot, and now I can release my mouse click. So now we have a solver configuration block. Let's see what is inside this block. So this is solver configuration. It defines the solver settings, and here we have so many parameters. Now what is the meaning of all these parameters? Okay, let's keep all this as it is, as the default value, and maybe if you are curious about knowing more, you can click on the help and try to understand what's happening and how to put all these values. But at this moment, let's keep it default value, right? Now, does it solve our problem, right? Now, are we going to have the diagnostic viewer or error coming up again? Let's try and hit the run button. No, probably not this time. Then, okay, what is the result? Okay, result is -10. Okay, here we are able to run our simulation of a lever perfectly. Why? Because 10 is the value of the force which you are giving, and 10 is going to be the force applicable at point A, and what you get at point B is going to be -10. So exactly the theory behind this applies, and now we are able to run this all equations, and we are able to get what is the value of the output force at point B. So this is our first simulation. And what will happen if you give some other constant value, right? What will happen if you give let's say maybe 100. Let's say if we give 100, the answer is again -100, because whatever the force you apply, if these two lengths are equal, then whatever is this 100, the negative of that, or whatever is the input, the negative of that will appear in the output. Now let me try with the 100 same value and change this to AC arm length to something other than 0.1. Let's keep it as 0.4. So now I need to press OK over here in order to get this change affected, right? You can use OK or apply. But if you double click on the block and if you click on cancel, the changes are not saved, right? So I'm clicking on OK, and now the changes are applied, and if you can check again by double clicking, and now it's 0.4 and 0.1. Now what do you think is going to be the answer? Now the answer is going to be exactly according to the ratio of this two lever length, and that will be displayed over here. So if we run the simulation, let's say our answer is -400, because the length is now in a ratio which is 4. So if you take this ratio, AC by BC is going to be the 4, and that is affecting the output. So this is how you can create a very fundamental lever simulation. Now there are so many other factors affected to it, where you may try to add some other things, right? Where you may have some other mechanisms affected. You may have some friction block, you may add some spring mass and damper kind of a thing, and try to visualize what is happening. So this is how you can create your first Simscape mechanical system simulation. Let's start another session with the Simulink. In this session, we are going to learn about how to create a more complex model, which is going to involve higher level of computations. So in the previous session, we have learned about how we can simulate basic lever mechanism with a fixed input. Now we are going to create another model with gear and wheel and axle systems. So how do we create a new model? So for that, you can actually click on the Simulink over here, as we discussed earlier, and create a new model. Or we have another option where you can click on the new button and select the Simulink model. So here is the another option where you can create a new Simulink model. So let's create a new blank model, and we want to simulate a gear. So with this session, I'm going to be a little quick in actually making a simulation or creating a proper simulation model for our exercise. So if you type a gear in the search box, what you see here is a gearbox, a worm gear, or a simple gear, planetary gear. Let me choose a simple gear. Now what you see is a simple gear. Now this is a simple gearbox which has follower and the base, and the teeth ratio or the gear ratio is given as by default value 2. Now in this case, it's also possible to implement the losses which are mashing losses and the viscous losses. So probably you can have a constant efficiency or the constant losses, or you can have the load dependent losses. And if you activate this, you can actually model the load dependent losses as well. So here you have the viscous friction coefficients, and their values can be also given in this array. So this is how you can implement the losses in a simple gear as well. So let's keep the default values, and in that case I need to press a cancel because I do not want any changes to happen to this model, right? So if I simply press cancel, there won't be any changes which will be applied to this block. With this simple block, we need to actually have a wheel and an axle system. So what are we going to do? We are going to give some input motion, and we want to analyze what is happening in the output when you have rotational motion converted into linear motion. So how can we convert rotational motion or angular motion to the linear motion? And that is possible with Simulink block called wheel and axle. So if you simply search wheel, it will come wheel and axle. So wheel and axle block is actually a block which will have the axle as the input, let's say coming out from the gearbox, and the P is nothing but a periphery. So if you double click on this block, here what you will have is the parameters, and you can understand about what is a wheel's radius and what is the mechanism of operation. So whether it is going to drive the wheel in the positive direction or the reverse direction or negative direction. So let us connect these blocks, and before we connect them, let's understand what are the basic requirements of the input and output side. So the fundamental requirements where we will give this simple gear as input is going to be the angular velocity. Let me search with velocity, and we want to have ideal angular velocity source, right? So we don't know in the previous case, or we are not very sure about how the angular velocity is created, and we just want to understand without worrying about the previous stage that okay, there is some amount of angular velocity given from the input side. So now I have connected the F block, which is the output of the gear, to the axle of the wheel. So I'm rearranging the blocks in order to simply have proper space management. Now what is this ideal angular velocity source? This ideal angular velocity source is going to give the whatever value of data we give to the S port, the same will be given to this input. Let's say for example we give 50 here, so 50 unit, it can be RPM or it can be radian per second, we have to ensure with this block. So whatever is the value given at S input port, that is going to be available to the B part of the simple gear. Now because we have connected this gear output or another shaft to the axle, now whatever is this speed, that will be the same speed, and this angular velocity will be converted into the peripheral speed, which is going to be the linear motion. So what we require here is a sensor which is translation motion or linear motion sensor. So I'm going to type translation and motion sensor, right? So if I type translation motion sensor, then we have something available over here. So now this can be connected with the input R, and V and P are nothing but the velocity and the position of the block. So here we are creating such a situation where you have some input data. Let's say here you have an engine giving, let's say 1000 RPM, and now that 1000 RPM engine is connected to the gearbox, and gearbox is connected to the axle, and now we want to analyze what is happening to the wheel, or what is the translation motion at the wheel side. So probably we are creating a very simple engine transmission system from engine shaft to wheel on the vehicle. So now what are the missing blocks required over here? So very first thing is we need to have a Simulink to physical system converter which will be attached to the input. So it's going to be, I'm typing here Simulink to PS converter. So because we are going to give some constant input to this through the Simulink, and that will be given to this physical signal. So we are converting the Simulink block to the physical signal. Now similarly, we want to analyze what has happened to the motion on the output side. So here also will require some output. Let's say we use a scope for the output. Now scope is a Simulink block and we can't connect directly with the velocity, right? So if I try connecting this, because this is a Simulink signal and this is going to be a physical signal, they are not going to be connected. So what do I need is a similar another converter, which is physical signal to Simulink converter, and then connect them together. Like let's say I'm interested in velocity and I'm connecting the scope to this part. So here comes our input and output. So let's say here again, before we do any changes, let me save my model, and I'm going to save in let's say D drive new folder, and my model name is a gear transmission. So now I have saved my model, and what are we missing over here? So probably we haven't connected the P port, and what will happen if we do not connect the P port? So probably you can check that in the help, and we haven't connected the C part of this and C part of this, right? So what is the C part? If you remember from the previous session, C is nothing but the common point or the fixed part, which is going to be the rotational reference. So we can have the similar reference frame for C connector of these blocks. So now we require some references for this C part of this block. So let's find out the rotational reference block. So we have a mechanical rotational reference, and let's connect the C part over here. And because we'll also require a solver configuration, otherwise our simulation will not be solved properly. So we are attaching this solver configuration to this part as well. Now we have another green part, which is a translation motion, and let's connect this C part to this reference as well. So when I connect this C part to this, it's not allowing me to connect. What is the reason why we are not able to make this connection? Because this is going to be a rotational reference. So if I show the block name, it is a rotational reference. So similarly, we need to have translation reference as well. So I'm going to search a block called translational reference. So we have a translation reference which is now with another green color, which is as per our requirements. So here we are almost ready to hit the run button. But yes, what is going to be the input? What is the value which we are going to give here? So let me give some constant value, and let this constant value be 100. So we are giving a constant 100 to this input. And now let me zoom out of my all the Simulink block, because we have now many blocks connected all together, and we are giving some 100 value over here, and that 100 value is actually given to this input shaft of the gear. The output shaft of the gear is connected to this axle, and axle is connected to the wheel as per this diagram. So now wheel is going to have its linear motion, and now based on the wheel radius, which is, let's say we keep it as 0.5 meter. Now with the 0.5 meter wheel radius, we are going to observe some output linear velocity, and it's okay, we can keep this position disconnected for a while, or if we do not connect this part as well, it's not going to give any error. So now we are ready, and let's hit the run button, and if there are any errors it will show up, or otherwise we are going to observe some constant linear velocity in the output scope. So now my model is being compiled, and yes, the Simulink has solved our model, and the scope is showing -25 constant value. So for 100 we are getting -25 linear velocity. So it is based on the gear ratio, which is actually the 2, which is dividing or a multiplication factor from input to output shaft. And here we have the mechanism, which is orientation drives in the positive direction. If we click on the negative direction and keep it OK, now I'm going to get +25 in the scope. So here we have scope connected, and this is a fixed input. Now every time we are connecting the fixed input which is not going to serve the purpose, or which is not going to be the more realistic case. So in the case of an engine, let's say it's an engine of an automotive system, and you are pressing the throttle and the fuel input is changed and the engine RPM is also changed. So now I want to visualize something, or now I need to check out what happens if we change the RPM at the input side. Now how do we provide the variable input? Now there are multiple options for that, and by your experience with the Simulink you will learn how to find those blocks which are going to produce the variable outputs, right? And one such thing is called a repeating sequence. So because I am aware of this block, I'm straightforward using it, but as a beginner you can try searching in the help file or in the Matlab documentation and Simulink documentation about how to produce variable input signal, or how to produce the signal which we want, right? So a repeating sequence is again, let's say, a Simulink block, and let's understand what is a repeating sequence. So this sequence is going to have time values and the output values. So it has 0 to 2 time values, and let's say output values or its signal is also from 0 to 2. Instead of 2, let's keep it around, let's say 1000. So what does this mean is, actually when you set all these values from 0 point, you are going to have the 0 output value. At the end of this time period 2 seconds, you are going to have 1000 value over here, which is declared like this. So whatever you are assigning, that will be reflected in the output, and this is nothing but a repeating sequence as shown in the block itself, right? So if I expand this block, whatever is the type of graph you are able to see, that is going to be the type of output. So probably now our engine RPM is linearly increasing every time, right? Every 2 seconds we are linearly increasing the engine RPM from 0 to 1000, and again it will fall down from 1000 to 0, and then again it will increase from to higher value near to 1000. So let's run this. Now because I haven't connected this block, I'm going to simply comment this block out. So how to do this? You just have to click on the percentage. So if you click, and there will be 3 dots on the block which you are able to see here, and you just have to select the comment out. Now I think we are ready to run with the system, and let's say our simulation runtime is going to be 10 seconds. So what is going to be the output available? So now because the engine speed is varying, or it is linearly increasing and decreasing like this, we will have the output also similarly fluctuating in the positive direction. So this is what we are getting in the output. So here we have the output coming up to 250 and then falling down and then again increasing and decreasing. Now another way to see the input and output together is to just create another signal out from this and connect it to the scope. So this is a simple way of looking at the input and output simultaneously and understand what is happening. So now if I click on the run, we are going to have input and output both in the same plot. So look at the input and output. If I click on the view and show the legend, which is this part, so now I am going to understand what is the meaning of this yellow part and the blue part. So I'm going to turn on the legend. The yellow is the repeating sequence, which is the input, and the blue is the output, which is PS to Simulink converter. So here the engine RPM varies from 0 to 1000 and it fluctuates like this. It is a repeating sequence, and therefore the actual speed, which is linear speed at the wheel periphery, that is also changing. Now what are the other input possibilities? So let's disconnect this one as well and try to understand what is the other possibility. So I'm going to comment out this block as well, and I'm going to use another block which will help me to generate a signal which is as per my requirement, and one such block is a signal builder block. So a signal builder will help you to actually create your own signal. So let me connect this signal builder block, and this is also Simulink block. So here you have a signal 1 connected to the input, and if you double click, this window will open up. Now what is a signal builder? So signal builder will help you to build your signal, and the default value is this kind of a red signal. So with this, it's 10 seconds in total, what you can see over here, and the value which is 1 for specific period of time, let's say from 4 to 6. So this is the default value of the signal. Now how can I change the signal according to my requirement? So I need to just go to this line and shift out this line, and now my signal is almost constant value 1 for most of the period out of 10 seconds. So instead of this, how I can modify this is to change the amplitude. What I can do is click on this particular point, and when I click on this point, now my point data or scales are going to be activated like this. So over here you can see the point is going to be activated. Now the time t is 0.69 and the value is 1. Instead of 1, if I want the value to be 10, I can click on just 10 and press enter. Now my value is 10, and probably the earlier value of this point was around 1, so it has been remaining the 1, and you can shift this up as well. So let's say now your value is decreasing, right? Now instead of 10 second, probably you can assign this 0 value at 100 second. So now I need to change this. I'm getting some error over here. If you see this error, the minimum display limit must be greater than or equal to minimum time limit. So how do I get rid of this error? So I need to change the signal properties, and which is from here. So how do I change it? I need to go to Excel axis and change the time range. So if I change the time range to, let's say, probably 100, now our graph is going to be up to 100. So now you can change it like this, and probably you can add many other points as well, right? And let's say at this point here you have the value which is something related to 5, and if I enter this, so now my value is 5, and you can probably change it like this, right? So probably I'm creating some random signal, and before I go to the main model window, let me save these changes, and let's simulate this kind of a signal as input to the gearbox. So whatever we have given, that is available as input, and let's understand what is happening, right? So let me connect this part to this as well, and let's see what is happening in the output. Probably if you have seen something wrong, which is over here, my simulation stop time is only 10 seconds, and here I made a mistake where I will not be able to visualize the signal which is built up to 100 seconds, right? So we need to ensure that we have built it, or we have generated the signal up to 100 seconds, which is this time limit. I need to change my simulation time as well. So let me run the simulation for 100 seconds and now hit the run button, and let's analyze what is happening in the output. So with this, we are able to get the signal builder block, which is the yellow part, and accordingly the blue is following with reference to the gear ratio and the wheel diameter. So now you play with the gear ratio and the wheel diameter, you will experience the output changes as well. So with this, I hope you are learning the different steps where you instead of having a constant, you can have a repeating sequence, you can have a signal builder as well, or there are many other ways as well. Now let me try one thing. Actually, I do not have the engine RPM fixed, right? So here we are giving the fixed input, and we want to actually change this to the runtime variable and give it as the runtime input. So how do we do that? So let me disconnect this part as well, and I'm going to comment this out because I'm going to use something which is going to be changed in the runtime. So how do we actually change the input during runtime? So for that, the simulator or the solver in the backend is going to work very fast. So I'm going to have, if I need to have simulation which is running for a longer duration so that I can change the input, I should write here infinite. So if I write INF, it is going to mean that the simulation is going to run until I'm not going to stop it, right? So this is going to be the case where it's infinite time allotted to the simulation solver. It's not fixed. It will run forever until the stop button is pressed. Now I wish to change this input while the simulation is running. So for that, we have an option called a slider gain, which is a gain block which can be configured like a slider. Now what is a slider? A slider is similar to, let's say, a throttle. Here you have a throttle or an accelerator pedal, and which is going to the engine, and the engine is producing various different RPM values, right? So this is a slider gain, and let's say its low value is 0 and the high value is, let's say, 2000 RPM, right? So these are the values which are given, and what is something related to the input, right? So if I click on run without giving input, it's going to give me some error, or I need to fix it up what is the value by default, right? So I'm going to stop the simulation and I'm going to connect some by default value over here, right? Or it's possible that you may not connect any input value. So let's connect this part to this one and let's run the simulation. So now I'm running the simulation, and look at the time over here. So what you see over here is the time which is varying, and this is going to be 84,647 seconds already elapsed. So now I'm going to change my input in the real time by changing the slider like this. So now I'm changing the slider over here, and my constant value right now is 660. So now I'm changing this to highest value 2000, and again bringing down. This is as equal as I'm applying the throttle while the simulation is running. So if I do like this, and if I press OK, the 1640 constant value will go, and let's stop it and let's see what is the result. So what kind of a result we are going to get in the output? So we have got something which is almost 0, and probably if we again rescale it with this, this is also going to show us the 0 value. So what is the reason? Because we have given a slider gain where we must have some default value, and which is undefined over here. So Matlab is not going to give you any syntax error if you have this block disconnected, but probably if you connect some constant over here, and this constant is multiplied with this variable gain, right? Now it is as equal as you have the variable values connected over here. So now let's run the simulation, and let me open up this slider gain and let me change all these values and try to run the simulation. So I'm changing this values very frequently from between 0 and 2000, and now probably my value is constant 360 for a longer period of time, and let's see what is happening in the output. So what you are able to see here is probably some constant values which is related to 360, and some blue line which is related to, let's say, less than around 90. So now if I scale it up, or this is the button where it is going to scale the limits of time and the amplitude, this is what is happening, right? So we initially started varying the RPM like this, and why do you think these are varying in the steps, right? Because we are providing the real-time input through a slider gain, and all these values are changing in time according to its sampling rate. So whatever is the sampling rate of the slider gain, that values are captured. So look at this values, and here is your blue output. So this is how you can actually run your simulation with the variable input parameters. So I hope now it's clear to you that how to provide variable inputs and how to use the Simscape mechanical fundamental blocks. In this session, we are going to learn about basics of subsystems and how we can manage very different blocks or many different blocks in our Simulink model and create some subsystems and write down some scripts, or actually try to link the scripts to the models, right? So let's try and learn about what are the subsystems, right? So before we begin, let me show you a very fundamental thing to be noted down is the directory path, right? So if some of your colleague or if some other person has given you any of the file, right, and you try to open that file, I think one of the way to open this file is to browse through the directory path. So the earlier files I have saved into the new folder, and whatever I'm going to see here is my gear transmission file, right? So here I have a gear transmission file, and probably I have 1, 2, 3, 4 main blocks, right? And these are Simscape mechanical blocks, and I actually want to just understand all these blocks as one system or as a black box and try to play with the input and output. So we want to have one input, one output, and try to see what is happening inside. So in order to compress our complex diagram, which is likely going to be the case where you have more than 10 number of blocks, probably you can zoom it out and use the other space, or if your diagram is not going to look it properly, which is this case, let's say I have something where this connection is not proper, or it may not be okay to deal with the diagram, right? Or if the diagram is very complex, it's not possible to deal with it, right, with some good accuracy. So what we are going to do, we are going to create all these blocks which are included here, and let me create a subsystem, right? So what we are going to do here is now create a subsystem of all these blocks. So how do we create it? So when we just select all the blocks and click on the 3 dots which are coming up, there will be an option of create a subsystem, right? So this is basic first option, create a subsystem, right? Let me do it again for you, and I just don't want to include the scope, and I just don't want to include the slider gain, so I'm just shifting them here so that they are not selected, and rest of the things, all things I want to include in a subsystem. So I think I have all the models, and if I create a subsystem, look at what has happened. So now all the blocks have gone into a subsystem, and we have number of inputs and outputs, right? So if we double click on this, we'll get to know what is inside the subsystem. Now if you want to go back, you have to just click over to the previous block, which is gear transmission, which is name of the file we have given. So now I'm back to the main model. Now in the main model, we have just one input and output, and therefore this can be like again simplified to a great extent. And if we have a subsystem like this, and if you have similar inputs going to other systems as well, where you can have another group of subsystem, let's say randomly, let me take all these 3 blocks which may not be actually relevant, we just commented them out, but create another subsystem, right? So we are creating another subsystem. When you what you have observed, when we create a subsystem, it is going to assign by default the output and input ports, and all the connections are going to remain same. So this is how you can create a subsystem. And if you want to just go back, you can press the Ctrl Z and see how the things were previously. So now we are again back to the same part, and I can press again Ctrl Y and see what we did, right? So the important keywords or important keyboard shortcuts are Ctrl Y and Ctrl Z, same as how you play with your Word file or the Microsoft Office. So whatever you have done, you can undo and redo easily. So this is the subsystem which we have created, and now there are various types of the subsystem. So we can actually make this enable or disable, or we can create a subsystem for selection, or we can convert this to a reference subsystem or a variant subsystem as well. Now, what is a reference subsystem and a variant subsystem? You can learn this in detail from the help, but effectively the variant subsystem is nothing but you create a gear system where you have a gear ratio and the wheel ratio like this. Now you duplicate the system and you have some other gear ratio with some other wheel radius, and that is your subsystem too. Now you just want to run a variant of a subsystem where the gear ratio and the wheel radius or wheel diameters in meter are something else. So here you can have another subsystem created, and you can disable this and enable the other one and easily switch between different types of subsystems. So I hope the subsystem part is clear to you. And now in order to learn more, let's actually understand about the complex mechanical engineering systems. So whatever we have tried to create it here is a gear and a wheel axle system, which is engine transmission system. And let's understand actually how the engine related systems can be modeled. So now I'm going to open up the Matlab documentation, and in the documentation toolbar I'm going to search engine. So the moment I search engine, there will be a drop down popping up like this, and we can have many different suggestions. So we have basic search with an engine, and we can actually make it very generic with reference to, let's say, some Simulink blocks of engine. So here we are getting many different stuff which is related to engine, because engine is a very common word which will appear in the search result. So we can type engine Simulink. So now with the Simulink, we have something related to mapped SI engine, map CI engine, and there are other related things as well. So here what we are able to see is many different types of engine related results. So here let me show you a simple SI core engine, and this is a high level model of an engine from powertrain block set. So powertrain block set is actually quite high level block set which is for automotive purpose. So here you can see what are the inputs and what are the outputs and what are the efficiency related equations, what is the air fuel ratio, what happens to the exhaust, how the power is calculated, and what kind of inputs are there and what kind of outputs are available. So here you can get all the information related to the engine. Now before we actually go with the powertrain block set related engine, let's understand a very simple engine block, or let's search in our model itself an engine block. So I'm going to here search an engine, and it's a generic engine, right? So generic engine is a very fundamental block which we are going to get, right? So let me search something related to generic engine in the help, and a generic engine is going to be a most simple block of an engine. So here you have the engine speed, throttle, power and the torque, and engine power demand and its curve, and whatever are the inputs and outputs and how these values are created, right? And in the help file you can get all the idea about the generic engine. So let's search again with this generic engine and understand about the search results. So what I'm trying to get is, let's say, let's find some engine related model. So let's find engine model. We actually are looking for the examples, so we can actually open and close the filter block from here. So let me use this filter and understand about some examples, and let me keep it like generic engine. So here is the automatic transmission controller, and if we open up this model, this is going to be a quite complex model. Let's try to run this model and understand what is happening inside an engine block. So the purpose of showing you this example is to actually understand how the larger system or how complex models can be built. So here what you see is the Manuverse GUI, right? So this is again a subsystem. This is engine is a subsystem. The gear shift logic is also a subsystem. The transmission system we just tried to create one is another subsystem, and the vehicle model. So here what you have is a vehicle model, and what you can see is all those parameters of a vehicle model. Now if we want to understand what is inside this, what we can do is click on this arrow which is appearing over here. So if you click on this arrow, it will show like look inside the mask. So you can see look inside the mask, and what is inside the mask? See, this is a vehicle model which is created by implementing the equations. So what you see here is the addition, the multiplication, some gain, and there is some another block which is linear speed conversion. So if I go back again, I can go back to the main file, like browse the depth of the model from this part, and if I click over here vehicle, or if I click over here, I will be again in the main block, right? So this is about the vehicle subsystem, and let's go into the engine subsystem, and what you see here is the engine torque. So what is this engine torque? So basically an engine is actually implemented as a lookup table. So what is a lookup table? A lookup table is nothing but the data which are given as the characteristics. So here we do not have any engine model, but you will be able to understand how subsystem creation will help reduce the complexity of your model, right? So here if you want to understand what are the maneuvers, right? So here is a throttle applied like this, and the brake applied like this. So this is again a signal builder block. You can apply multiple signals as well, right? So this is a signal builder block, and probably how it looks different, right? Probably you can change the name like this, and you can change how it appears as well from like this, and instead of signal 1 and signal 2 you can use the throttle and brake signals as well. So this is one example of what subsystem is, and in fact you can study about the how Matlab has created all these models by looking into a subsystem. So let me show you how. So I'm again going to the model which we created, and I'm interested to understand what is inside this generic engine, right? Or which are the other blocks which are implemented inside the generic engine. So now I want to see inside, so I can right click over here and actually press look under mask, so which is the control U. So what you see here is a mask, and you can look under the mask, and if I select this object and press the control U, you will be able to see the block properties from inside. So this is a Simulink block, and you will not be able to see because it's a Simscape language, and if the model is built with a very fundamental Simulink blocks, you will be able to see what is inside the block. So let's take some other block and let's try to understand how it is created. So let's try to have a vehicle body. So let's understand what is a vehicle body. So vehicle body is another block. Let me show you properly. So this is a vehicle body block, and if we again press Ctrl U, because it's a Simscape block, we'll not be able to go inside and see its definition or see its model, right? So let me select some other block which is other than the Simscape. So let's have some gear. So here we have a gearbox, which is a foundation library, mechanical, and it is again a Simscape model because it's a green color. So let me search out some other block and let's find out how these blocks are created by the Matlab. Let's understand how Matlab has built subsystems and how the larger blocks are created from the smaller blocks. So I'm going to use let's say we go to the aerospace block set, and in the aerospace block set let's select the aerodynamics. So in the aerodynamics we have something called as aerodynamic forces and moments. Now this is going to be the fundamental Simulink block, and let me add this block to our model. So we can click on this and Ctrl I will add to our block. Now here, when I have added this aerodynamic forces and moments, I can actually configure this block by what are the input axis, force axis, moment axis, and what are the criteria, right? Now if I want to understand how this block is created and how this block basically works, so what I can do is right click on this and check out this mask option. So if I right click and check out this mask option, and we have something called look under the mask, and if we do this we will be able to understand what is under this block. So if I press Ctrl U, now we are at a next level of model. So this is how the Matlab has created the aerodynamic forces and moments block. Now basically these are all Matlab fundamental blocks, and if you double click on this you will be able to see what are the other systems inside. So here you will be able to understand what are the other parts. Let's say here is a cross product used, here is a moment transfer, and these are the inputs which are actually used for the blocks. So if we again come back to our main system, here we have this block, and basically the subsystem hierarchy is going to help us to model all related blocks. But remember, the Simscape is such a language which is different than a Simulink, and you will not be able to look under the mask. Sometimes there may be some blocks which are, let's say like this, which will allow you to see the source code. So here you can click on the source code and it will open up. So this is how the Matlab hierarchy works out for subsystem and system level. Now let me delete this block and actually understand how we can do the experiments now, right? So we have something available over here as the gear transmission block, and let me delete this subsystem as well. So now my model is clear, and we have a subsystem, and we can rename the subsystem as let's say gear and wheel along with the axle. So here we have the name gear and wheel given to this subsystem, and we can probably change this names as well, and we can assign some image to the subsystem as well. So instead of the block which is displayed like this, we can actually assign some image, and for that you can refer the help. Now what I want to do next is, instead of going into the subsystem and each time changing this value to, can we do something where all these variables are defined in a way that they can be changed from somewhere else? So let me explain you what exactly is the meaning of configuration of model parameters. So for example, right now, these are the only two blocks which you have. And if I create another subsystem, right? So here you have another subsystem. So now when you go inside this, you have to go inside another subsystem and then double click on this and then change the value this 2 to your new experimental value. So instead of going into the depth of the model, let's say the level 1 and level 2 and then changing the value, why can't we create some variables where this value can be referred to, and that is going to make our task easy. So now we are going to discuss how to manage the model settings, right? So whatever are the model parameters, how we can actually manage them. So let me show you a simple block where the teeth ratio is 5, and basically we want to do an experiment where we continuously vary this value from one experiment to another experiment, right? So every time it is required to open up that model, and which may be inside a subsystem of another subsystem, right? So you have to go to that block and double click on that, and then only you will be able to vary it, right? So it may be tedious because this is going to be the case where you have the block parameters. Maybe you have many number of blocks available, and maybe instead of just one, you might have, let's say, 5 number of parameters to be assigned per block. And if you have 10 such blocks, probably you are going to assign 50 such values. So it's going to be really tedious in this case. Now, when you are going to do the experiments, you have to remember all the values, all the parameters, and record the results. For example, in this case, let's say the gear ratio here is actually going to be varied from 5 to 10 to 15, and then finally 25, and maybe so on, so other larger values. If you are changing this gear ratio and analyzing the output values, which is output value 1, output value 2, and you are preparing a table or maybe a result table, then it's going to be difficult for you to every time do this exercise by writing here updated values. So what are the options? So how we can actually deal with this? So here there are many different options. So the first is we can actually connect the script data to the Simulink model. So for example, instead of 5, I can assign here gear underscore ratio, provided the gear underscore ratio is defined or is assigned variable in the workspace. So if we have a simple workspace variable which is equal to gear ratio, then we need not to go to the subsystem and write down the values manually, right? So let me actually do it with our block and help you to understand this. So now we are inside a simple gear and transmission file, and this is a model which we created, and there are 2 subsystem levels, and let's say here is the main file, right? Or here is a main block. Now we want to assign something to this gear ratio and something to this wheel radius. So let me write here wheel radius as radius. So I'm declaring this as radius, and let me use this simple gear. Now the moment I declare this as radius, it is going to give me some error, right? So what is that error? Basically it is giving me that unrecognized function or variables which are assigned inside the block, and there is an error. So before you hit the run, your Matlab is so interactive that it will help you to identify any errors prior to you press the run button. Let's take care of this, where we have given this as radius, and we need to declare the radius somewhere in the workspace. Now here the gear ratio, let's say this is GR. So now there are 2 parameters, one is GR and the radius assigned over here. Now let me go to the workspace. So how do you get the workspace? So workspace is somewhere over here, which is like this. And how to create workspace variable? So there are many different techniques of creating the workspace variable, and one simple is you create the variables like writing in the command window itself, where let's say gr is equal to, let's say, 8. So now we have created a workspace variable gr equals to 8 over here, right? Now let me create another variable by typing the radius equals to, let's say, 0.3. So now we have a radius variable also created in the workspace. Now let me check with my model, and probably now this models where the radius and the gr are declared, they are now not showing any more red, right? Because the Matlab has taken all those variables from the workspace, right? So now if I run the simulation, I will be able to simulate my case with the previous values. Here we need to remember that because we were earlier running this in infinite mode, I need to press stop and understand what are the results. So with the given values of radius and the gear ratio, this is what we are getting in the output. For the fixed value of 360 input, we are getting somewhere near to 10 in the output. So probably this is the most simple way of creating the variables. Now let's say here we are dealing with the two variables only, right? So instead of two variables, and if we have a fairly complex system where we have around 50 variables, right? So it's always better to handle all this in a script file. So let's now learn how we can associate a script file to the model file, right? So let me create a new script. So here we have a new script. Let me save this as the parameter of the model which is related to gear, right? So gear parameter .m file I'm going to create here, and instead of typing all these parameters in the command line, let me clear all this. So here you can clear the workspace, and once you clear the workspace, all these variables will be deleted. So now instead of actually writing all these parameters in the command line, we can write down all those variables straightforward in the m file itself, right? So now let me write a script where my radius equals to 0.9 meter and my gr value is equal to let's say 5, or let me keep it as 25. So now I have saved this file, and now let's go to our model and let's try to understand what is happening. So now I'm going to keep the simulation time which is fairly 10 seconds over here as highlighted, and let's see what is inside. So now again we are getting something unusual, and probably here you see the red color highlighted block. Now we have declared an m file, and probably the same variables we have assigned. I think I haven't made any mistake in typing as well. If you have a capital R or maybe some other spelling, then it's also not going to recognize. But I think radius is what we have declared in the m file. Okay, here you can see what we have declared over here. So what is the reason why we are not getting it, and what will happen if you click on run button? So let's go to the main diagram, and if we press the run, there will be some errors in the diagnostic viewer that the ratio and the other parameters are not declared, right? So this is what the error we are getting. Now the simple reason is your variables are not in the workspace, right? It is very important to understand how you can get the variables in the workspace. So probably we have typed this m file, but we didn't click on the run, and therefore we do not have anything in the workspace, right? So if we click on the run, this script file is run, and now we have all the workspace parameters listed over here. And now I think with this we will be able to run our simulation. So let's try and run the simulation. Okay, now there are no errors. and we are getting the output results according to the values which are declared in the script file. So now with this, it's now clear that how we can use the script file to parameterize the model. And an important point to remember here is to save your script file and press the run button before you run your model. So it's very important to run script file first and then your model, because the variables which are available in the workspace, that will be only correlated with your model. Now, what are the things you need to keep record of? So remember, whatever we have files, let's say our gear transmission is a model file which we have created, and the parameter underscore gear.m is in the same folder, D drive new folder. So if your directory path is something different, then it is not going to work out. So now let's understand. Now we are going to see something else where we can use the Simulink block to create variables from the block itself, right? So instead of actually typing the script file, what we can do is, let's say we have a constant block like this, and this constant block is assigned some value 50 over here. Now instead of the 50 defined on this block, we can create a variable which is named as, let's say, engine RPM, right? So here we have the 3 dots, and if you click on this, you will be able to create new data, and that new data can be created either in the model workspace or the base workspace, and you can assign the name over here, right? So let's do it in the our model itself, and let's try to understand what will happen. So now what you see probably over here is with the Simscape blocks, this part is not available, right? So the Simscape block, probably you need to go with the scripting, and that is the better option. And for Simulink, it's possible to get it done by the values which are actually created in some variable way, right? If I double click on this constant, what we have here is the constant value 1 assigned over here, and if I press over here, which is highlighted part, then I can create a variable as well. So if I click on create variable, then I can give the name as let's say RPM, and the RPM is going to be saved in the model workspace, and we are creating this variable which is RPM, and which is now reflected over here and over here as well. So now we have created RPM, and instead of linking from the script or the workspace, it is now possible for you to link it from the block itself, right? So we have created something called RPM, and let's see what is happening in the model workspace. So if we refresh the model workspace, and if we run this part, or if we type this RPM, probably the RPM is not recognized, right? So here it's going to be the fundamental workspace or base workspace, and let me change it to the fundamental workspace. So here we have an RPM variable, and it is in the model workspace, and we can open this and we can change its value from over here, right? So you can change its value from here, or we can actually explore this in a model explorer. So what is a model explorer? Model explorer is basically going to open up all the values, and where you will be able to see the workspace which is related to the model. So here you have the model workspace which is related to the gear transmission file, and its value is 1 over here, as you can see, and you can modify from here. Now with this basic understanding of the model workspace, we can actually let's say delete this part and assign this as a constant 1, and now let's say try again with a create variable. So now I'm going to create a variable again with let's say revolution, right? And let it be defined as a engine revolution, and I can create in the base workspace. So we have created something called a revolution in the base workspace, and let's check it out over here. So here now in the base workspace, here we have something available as a revolution. So the important point to be noted down here is there are two workspaces for the model. One is the base workspace, which you can see from the command window, and another is the model workspace, which you can see from the model explorer. Now what is exactly the model explorer? You can take the help and type here the model explorer, and this will help you to understand how does the model explorer work. So here you can click on the model explorer view, and what are the meaning of all parameters, right? And how to utilize the model workspace part. So here is the important help where how to use the model workspace that is defined, and probably the model related data, and you can make it separate, right? What is the purpose of having two workspaces for the model? Basically, when you have something related to a complex model, when you would like to declare the variables which are related to models only, and you do not want your base workspace to be affected by this, right? And in that case you can use the model workspace, otherwise you can use the base workspace as well. So here we have a revolution defined as a base workspace, and its value can be changed from here itself, right? So you can change the value 1 from here itself, right? And now if I type something called revolution, then the command line is going to understand what is the value, and the revolution 1 is available. So probably I can assign something in the command line itself, or maybe from here itself without actually opening up. So when you click on this and add the editing remark, you can change this value and probably let's say make it 10. So now the revolution value is 10. So now I hope you are able to connect the script data with the model parameters. And this is going to be very important exercise when you deal with many number of parameters and many number of models where you have such a complex model of a system. Hello everyone. Now we are going to start modeling an important system which is a fan driven by a motor. So here let's say we have a fan which is controlled by a simple motor which is a DC motor. So this is going to be a good example of an electromechanical system where electrical control of DC motor will result in variation in speed of fan which is connected on the shaft of the DC motor. So we need to understand first what is exactly the behavior of a fan load from the DC motor perspective. So usually the fan load or torque exerted by the fan load, let's call it as TL, the load torque, which is proportional to the square of the speed, which is omega m. So the load torque is proportional to the square of the speed. So usually this is the case, and let's say the constant of proportionality is C, then it is going to be C times omega m square, and this is expression of TL. Now based on the value of C, you can actually model a fan load, and you can apply various voltage and current at the motor side and change the speed of the fan. So here we are interested in simulating such a system where we are varying the voltage and current, and this voltage and current, which are electrical quantity, will affect the load torque and the load speed. So let's assume here we have a motor and its shaft is connected to a fan. So fan is nothing but a simple construction. Let's say it's an exhaust fan or simple ceiling fan having, let's say, 3 number of wings. So this is a fan load which we are required to actually simulate, and this fan load, according to its aerodynamic characteristics, is going to have different speed and different torque values. And also we need to consider whatever is the inertia of the fan load. So basically this torque speed characteristic can be modeled in a Matlab environment like this equation is the first one, and we can have inertia also added, which is going to be the weight of all the wings of the fan and maybe the rotor inertia of the motor as well. So here let's say this is a DC motor and we require a DC supply which is going to power it up the motor. So motor is driven by this supply and voltage and current are going to be taken from this supply voltage. Application, where you will find this kind of an application in reality and how you can actually simulate a more realistic situation. So this is just an image of a fan which can be an exhaust fan or any other type of a fan where you have some 2 terminals coming out of this, and here inside of this is going to be a motor. So on the central part here, this is going to be a motor and which is given the supply from either AC or DC. That depends on the type of the motor. So let's go to the Simulink environment now and simulate this situation of DC motor driving a fan load. So here I have taken a subsystem which represents a fan load, basically an aerodynamic drag. Let me show you what is inside this subsystem. So here these are the 2 connectors R and C, and basically they are physical modeling connection port of the subsystem. So R stands for the rotating part and C is a casing part which is going to remain fixed. So here we have implemented the square law, which is the speed omega and the torque are correlated by these equations. What you see inside another subsystem is just the multiplication of omega with itself, and therefore you have the omega square and a gain which is a constant of proportionality and which is this value minus 8 e raised to minus 8. So here if I go one level up, then we have this system where this is nothing but an aerodynamic drag block, which is the name given to this block, but actually we have used this block earlier and it's a torque source. So this ideal torque source is going to apply torque on the shaft of the DC motor according to the speed of the load. Now how do we get the speed? So for getting the speed, we have a motion sensor, or this block is ideal rotational motion sensor. So the value of the omega is given to this block and the value of the torque is given to this block, and therefore completing a loop. Let's come out of this system and we are going to connect R with the rotating part and C with the casing of mechanical system. So let me keep this block over here and now take a DC motor from the electrical Simscape toolbox. So here we have a DC motor. From its block diagram you can see these are the 2 brushes and the armature of a DC motor and the positive and the negative terminal for DC supply, and C and R are nothing but the mechanical terminals, or we can say mechanical ports. So let us connect R with this R and C with this one. So here I have connected R and C. Let us take a DC supply which is going to give some DC voltage to this motor. So I have searched DC supply over here. I am not getting any result. Probably I need to search out with a better technical keyword, and which is nothing but DC voltage source. So here we have a DC voltage source, and let me connect with negative, and in positive I want to read out what is the value of the current taken by the DC motor. So for current I need to have a current sensor or an ammeter, which is, let's search out for the current sensor. So here we have a current sensor, and we need to make sure that all blocks which are of equal color, they are connected together. So here this current sensor is also in the blue. Probably if you have any other ammeter or a current sensor which is going to be different one, then you will not be able to connect to this blocks. So here I'm making a search again, and there may be a current sensor of 3-phase type, which is not the case right now, or let's say a current measurement system. Then we will not be able to connect this one, right? Let's try see whether we are able to connect it or not. So for time being I'm disconnecting this, and let's understand what is the difference between a current measurement and a current sensor. So if we connect this one with this, we are not able to actually get it, because this block is basically from another library, and it is from a fundamental Simulink library. So here, and this one is a Simscape library block. A Simscape library block will be able to connect with the Simscape one, not the Simulink one. If you need to connect, you will require Simulink to physical signal converters. So I'm going to clean up my diagram, and let me make it a little compact. And here we have an electrical system ready and a mechanical system also ready. Now out of this, what we need to measure is, let's say, keep track of voltage. We are going to fix up the current and speed and torque. So let's connect the current over here. If you see, I'm not able to connect properly to this scope because it's a physical signal, it's not a Simulink signal. So what we need is basically a physical signal to Simulink converter, and then give an input to this and take an output like this. So here we have a physical signal to Simulink converter. So here we'll be able to read out the current. Now let us plot some other values which are speed and torque, which are mechanical. So I'm interested to plot speed and torque of this subsystem. So I'm going to go inside the subsystem. I want to get signal which is speed over here and torque over here. Now how do I connect all the signals outside of the subsystem? So there is an easy way of doing this, where you cannot route your wires, or where you cannot route your connections, whether they are electrical, mechanical, or any thermal or whatever, but they are in different subsystems. So here, if we want to get out these signals, we have to send those signals to another point, right? So once you have a complicated system, or once you have many such signals inside each subsystem, you are going to have trouble of taking those signals out. So they are not just like a port, but instead of a port, and instead of keeping it as a connectors, we can keep it as go to and from as well. So here I want to send this signal to outside. I'm going to write a go to is nothing but a Simulink routing, where we need to give it a proper name, and that signal is going to be available to whatever point we want to send it. So we are going to send the speed command, and let me connect the speed to this. And because we do not have the physical signal connection, we need to require a physical signal to Simulink converter. So here I have PS to Simulink converter for one go to block, and I'm going to copy with a right click for torque block, and I can copy this another go to as well. So here we have, when you click on the go to, you need to give a tag which is going to be referred elsewhere. So this tag is nothing but a name given to a signal, and you can refer it elsewhere, anywhere in your diagram. So here I have a goTo tag A. I'm going to connect torque over here. So I'm going to write torque. Okay. So here is a torque, and this one is the speed. So I have assigned the name of these two different tags, and now I can probably connect like this and like this through this physical signal to Simulink converters. So now I have sent these two signals, and let me get these two signals out near to this scope. So in order to receive those signals, we can write from. So from is another signal routing component which will help us to plot all the quantities at the same time. I'm going to take one from and another from, and I will be connecting to the scope. So here in the from also I need to assign the goTo tag. So my tag name is, let's say, first is speed. I need to remember the upper casing and the lower casing because I have typed the capital S for speed tag name. So I need to assign that like this. So I have a speed tag and a torque tag. So all the speed and torque will be coming over here. Now what you see highlighted in this from block is no matching goTo block. So what you see here is the goTo and the from are not matching, right? So probably let's go inside the subsystem and try to figure out what is the issue. Here we have a speed and the torque, and the names are exactly same. So here I have a goTo tag. Okay, the mistake which I am making over here is the tag visibility. So the tag visibility is local as of now, which means in a typical subsystem or within a subsystem it is going to be visible. So if I change it to be global, then the speed will be taken care. I need to also change this torque to be global as well. So now here we have the torque and the speed all together, which are actually going to be now reflected in the main diagram, right? So probably as you have a mechanical subsystem, if I have another complex system where it's maybe a DC drive or a DC controlled supply driving a DC motor, then you have an electrical subsystem as well. So when you have many such subsystems and you want to plot some results, or when you want to refer some signal from one subsystem to another subsystem, you can make those signals as global. So here the from and the goTo are the very important parameters or very important components for signal routing. So now let me configure the DC voltage source. The default value is 0. Let me keep it at 100 volt. Let's open up the DC motor parameters. So what you see here is the model parameter by equivalent circuit, and the armature resistance and inductance. I think you can refer it more detail with the help, but the fundamental important part is the back EMF constant, which is this value, and which is its unit is volt per RPM. So per revolution it requires around this much of volt, and that is a default setting. So let me keep the default setting over here, and as I said, we can actually connect some inertia over here. So let me find out the inertia block and connect it to this point. So let me rearrange the blocks again. So here I can just clean up my diagram, and I can connect the inertia by rotating it with Ctrl R, and probably I want to connect like this. So here we have an inertia, and let me keep as a same value, 0.01 kilogram into meter square. So this is going to be a inertia along with the aerodynamic drag, and which is connected to the DC motor. Now speed and torque are available. Let's run this simulation for 20 seconds and let me save into my folder where it's a new folder, and my file name is DC_fan, so that I will remember what is this model file. Probably if I hit the run button and almost everything is ready, we are now waiting to see the current, speed and the torque. So let's see, let's compile the block diagram, and probably you see many errors over here. So what are the fundamental issues, or how do we actually read out this diagnostic viewer? So here is an important line: each physical network must be connected to exactly one solver configuration block, and we do not have any solver configuration block. So probably we require a solver configuration, and so let me connect the solver configuration over here. I also have not connected any references, so whatever is the current, voltage and speed and torque, they will be with reference to some point. So we need to figure out those points. So I need an electrical reference, or it is technically called a ground connection. So here I have a ground connection. Probably this one is a black. I will not be able to connect with my Simscape block. I need to find another ground. So let me find out another ground, and here probably you can check out which library this block belongs to. So this is going to belong to spatialized power system, fundamental blocks and elements. So let's select this ground. So this ground is also black, and we need to figure out something else. Let's say electrical reference. Okay, now here is an electrical reference which is blue color, which is matching with the Simscape. Okay, fine. Look at these two blocks. They are exactly similar in symbol. They are also similar, but we need to figure out what kind of simulation we are doing. And if we are using all Simulink blocks, which are basic Simulink black color block, we can connect this ground as well. But right now we are using the Simscape, and therefore this ground will not be able to connect. Another reference point for this casing is to be a rotational reference frame. So I'm going to connect this with a rotational reference frame. So here is the rotational reference, and this reference I need to connect to the casing part. Okay, my diagram is now looking okay to hit the run button. But let me do one thing. It may not be quite aesthetic, or it may not be like quite good in terms of where you connect this wires, this connectors, and this maybe scope and everything. So what you can do is you can go to format and use the auto arrange block. You can go to format and use the auto arrange block, which is going to make the layout simple. So if I click on auto arrange, probably my blocks are arranged properly. So if you have a lot of mesh with your connections, let's say this one is going up like this one is also you have connected like this, and it's probably not perfect, right? Then the auto arrange is going to short it out. Okay, so with this arrangement, we are now ready to hit the run button and see the output. So here we have the output, and you can see these three signals which are coming like this. Now, do we have any idea about what color represents which signal? So what's the solution? Yes, you go to view and show the legend. So you have to click on the legend over here and you will be able to see all these signals. Now whatever has come over here is all PS to Simulink converter. So let's go back to our diagram and actually name them, and so that we are able to signal them properly in the scope as well. So in order to name a typical signal, you just have to double click and type the name. So here I'm writing current. So you double click on the line and type the name you want to give. So here let me make this scope a bit bigger so that we can see the names of the signal. So here I'm going to give a speed signal, and I double click over here and I have a torque signal. So now let's run the simulation and let's see the output. So here, yeah, your speed is increasing. The torque is like this, and you can zoom in with the torque, and let's see what is the exit torque value. It's a little negative value coming up over here, and if I zoom back again, the current is almost constant at around 25 and 26 between these two values. So this is what is happening with the speed. Now what we are doing here in this diagram is actually we are applying a fixed voltage which is going to result into the fixed value of the current, and because we have an inertia load, we are going to observe the change with the inertia as well, right? So this is 0.01 inertia we have connected over here. If I disconnect this inertia, do I going to have any different observation? So okay, let's keep this in mind. We have this variation of speed and torque and current, where the speed is continuously increasing, and let's try to understand what happens without an inertia. So here I have deleted the inertia block, and I'm going to run the system again, and let's see what is happening. So what has happened to the speed is now almost constant. So because of the inertia, the speed was gradually increasing. But now we have this RPM, or let's say speed unit, in terms of around 469 units. So this is the effect of an inertia. If you change an equation over here in this subsystem, or maybe the gain over here, and maybe if you want to implement some equation like 3 plus omega m square or 3 plus 2.3 omega m square, you will be able to do it. So let me go back to the main diagram, and instead of a fixed voltage source, let's disconnect this and let's connect a control voltage source. Now why do I need to connect a control voltage source? I just want to imitate, or I just want to realize a situation where we are gradually increasing the voltage, right? So what will happen to a DC motor if you gradually increasing the voltage? Its speed will also gradually increase, and here we have taken the torque which is proportional to square of the speed. So let's see what happens when we change the voltage gradually, not fix 100 voltage, but let's say we want to increase the voltage in the step of 5, right? So let's say every second the 5 voltage is going to increase. So that is a linear voltage rise, and let's understand what will happen in this case. So here I have a control voltage source, and probably this one is a black. I'm not going to try connecting this one. So let me find out another control voltage source, and let me check out this time about the foundation library. Probably this one is going to be the best suitable, and I can connect like this. Okay, so my negative wire is connected, and I can actually route another signal as well. So what is a control voltage source? Basically it takes an input from here, and whatever is this input, that will be the output voltage. Here the fundamental output voltage V equals to Vs, where Vs is the numerical value which is given to the physical input port. So now I can take up a ramp block. What is a ramp block? Ramp is nothing but going to continuously increase the value according to the slope. So here what I want is, in the 20-second time, I want to rise the voltage from 0 to 100. Instead of fixed 100 value, we want it to rise from 0 to 100. And what is going to be the slope in that case? It's 100 by 20, right? So we want to get 100 voltage at the end of 20 seconds, and therefore the slope is 100 by 20, which is 5. So I keep this 5 and let me connect over here. Okay, again a mismatch because it's a Simulink block and this is a Simscape block. So what we need is Simulink to physical signal converter. So here I have a Simulink to physical signal converter, and let me connect these blocks now. And probably what we have done is changed a DC supply voltage which is going to rise from 0 to 100. Now what will happen to the fan load? So fan load speed is going to change, and it is not going to be the steady speed from the beginning, and at the end of the 20-second we'll get probably the highest value of the current and the speed. And let's observe what is the torque coming up. So let me simulate this again and let's see the results. So here is the result, and probably what is the nature represented by this blue line? So the blue line is basically the speed and the orange is the torque, and what we are getting is some relation which is exponential, right? So because we are increasing the voltage like from 0 to 100, and the current is also increasing like this. So let me zoom in with the current, and the current value is around 25 ampere. So which was the earlier case where we supplied 100 voltage directly. So in this simulation we are able to understand what will happen if you change electrical parameter to mechanical parameter. So whatever are the effect on the mechanical things, that is what we are observing. And probably the exponential nature is coming up due to the equation we have implemented as speed and torque. So look at your torque value, which is going almost constant. Your speed is rising exponentially. And now if you plot, or if you see the relationship between the speed and torque, one value being fixed almost and the other increasing, this is going to be a square relationship. So this is about the DC motor based fan. And what is the effective learning outcome is how you can use the Simulink signals to apply a control voltage source, how electromechanical system works, and how from and go to are utilized here for subsystem signal routing. Thank you. Let us now have a look at a fairly complex model. I have opened up readily available engine cooling system Simulink model, and what you see here is a combination of some green part along with orange one, which are nothing but the thermal part. So an engine cooling system is actually modeled like this, and probably with visual inspection or just by observation you will be able to understand what is happening over here. So this is an engine block. Here you have an oil pump, and here you have a coolant pump. This is an oil coolant heat exchanger, and this is a radiator, and there is a fan over here which is implemented by this fundamental blocks, including the lookup table. So basically what is a lookup table? It can be a table which will give you the data, or which will actually be the comparisons or the functions for what value of the pressure or for what value of vehicle speed, what is going to be the output case, right? So with the given inputs let's say the vehicle speed and the fan, then based on this U1 and U2, what is the output, right? So that is implemented as a 2D lookup table. And if you see the air related system, which is fairly based on the fundamental Simulink blocks. So what you see here is the area air, and that is something related to what we discuss as defining the variables as part of the script or the model workspace. So here we have an engine cooling system, and because if you see this cooling system is fairly simulated for 15,000 seconds, and which is going to take much amount of time because there are so many parameters or so many equations to be solved by the Matlab, and it has taken so much of time. But the point I'm trying to explain you here is how to visualize the results, right? So look at the engine cooling systems, right? So here we have many parameters, and we have many other things like a cylinder wall temperature, and this is what is the plot of cylinder wall temperature at the end of 15,000 seconds, and which remains continuous to almost constant to around 95 degrees centigrade. So this is the overall simulation, and this is just one parameter, but we'll be able to get so many parameters and their results plotted by Simscape Result Explorer. So what is a Simscape Result Explorer? So let me open the Simscape Result Explorer for this part, and that can be opened by using this part where you have the model properties, and here you have the Simscape Result Explorer. So all those results will be available over here, and they can be plotted like this. Or it is also possible to use this script or use these commands to plot, let's say, the density of coolant, or maybe you want to plot some temperature and mass flow rate. So if you plot some temperature and mass flow rate and the coolant density, these plots are going to look like this. Now you may be surprised that the Simulink results are now different, right? So here we have this one window, and other one is this window. So this one is a normal scope. So this is a scope output, and the other window which you see is a Simscape Result Explorer output. So what is a Simscape Result Explorer? Simscape Result Explorer is another important feature where this is how the window will look like when you open up the Simscape Result Explorer from the previous command. Now what you have to do is you can actually see all the parameters, right, from the engine or maybe the cooling system or maybe any other system, right? So let's say you plot some heat to oil, and that I parameter is plotted like this. And probably if you are interested in radiator for cooling, and all your radiator related parameters are plotted like this. So Simscape Result Explorer, which is this window, can be effectively and efficiently used to visualize all the parameters. So whether you plot it or not, the Simulink in the backend is going to have all the record of all the data, all the models, and all the parameters will be available for us to visualize. So this is about the Simscape Result Explorer, and if you go in detail, probably you can see many parameters, right? So what happens to the temperature of the tank, what happens to let's say the P parameter, it remains almost constant, what happens to the U, and what is happening to the volume, right? So all these parameters are available over here, and you can visualize them from here. So this is just the introduction to Simscape Result Explorer. Let us now learn how we can actually input the parameters from various options. So one thing is, whatever we have learned is actually how we can use the script file and the workspace itself to input the parameters. The other important things are we can actually use the Excel spreadsheet as well to input some of the important parameters. So if you have an important data in your Excel sheet, it can be directly imported to a model. So let me open a new Simulink model, and in this model what we are going to use is, let's take help of spreadsheet and we can use it as from spreadsheet. So this is from spreadsheet option available, and it is also available from the workspace, right? So if you have some data already available in your workspace by your script file, you can use the same workspace variable or data to the model itself. So let's now learn about from spreadsheet and from spreadsheet. So now let's use the Excel input, and what we have to do is just from Excel or from spreadsheet, and we have to give the file name, and let's say file name is 1. So we have the file name. I think I need to give a proper extension also, so I'm changing it to 1.xlsx. so this is going to be my Excel file, and maybe you are wondering that where is that Excel file, right? So right till now I haven't created it. I need to create it in a folder where I'm going to save this model, and this is going to be the input from the Excel, right? So if you double click on this, here you have the file name, and if you click over here you can open up the folder as well. So we have opened up the folder. It's a new folder, and let me create a new Excel spreadsheet which is 1, and this is going to be the case. This is how I can link as well. So probably now we have created the Excel sheet 1, and make sure that the output data type is also like auto. You can change the data type as well. You can change the interpolation and extrapolation related parameters from here, and you can treat the first column as time as well. So let's now input some data in the Excel sheet and enter some output values. So now here I am in the new folder, and it's 1, and I have opened up an Excel sheet 1, and here I'm going to enter some data. So let me enter some data as time. So let's say we are having the time variation from in the step of 1, and that is up to, let's say, 104. So I have created 104 number of time data points, and I can now enter probably any other values. Let's say here are 2, 4, 6, 8 and something like that. So here I am entering continuously increasing values. Let's say I'm doing it up to, let's say, 31, and after 32 I have now again a linearly increasing value. Let's say 1, 2 and 3. So this is how I am inputting my data, and this is just a random input just to see how the Simulink treats this data. So we have saved the one file, and now we are ready to go back to our model, and here I'm going to save the model as let's say test with the Excel. So it's going to be test Excel, and now I will actually add up the Excel file over here, and I want to see what is the output of this Excel. So I'm going to directly connect this with the scope. So what we are going to do in this simulation is just plot all the values, right? So we have something the data related to up to 104, so I'm giving the stop time to be 110, and let's run the simulation and see what is available in the scope. So now my Excel sheet has been read, and here we have the output data available. So initially it went up to 60 at a faster rate, and now then it started from 1 to 3 and it went up to 80. So this is what we have given as the input data, and this is what we get in the output. So you can use the from spreadsheet as well, and in the similar way you can actually export the data whatever is available from this data logging as well. So you can use the data logging and you can get all your data in the workspace. Let's do it for one of our model. So I'm going to open up the gear transmission block again, and whatever is the output data, let me run this simulation. So we are running this simulation, and whatever is data available from the scope, that can be logged into the variable. So here is how you can use the data logging. You have to use this configuration properties, and from here you can go to logging and you can enable log data to workspace, and it is going to be a data set. So the variable name is going to be scope data, and now you have to run the simulation again, and the scope data will be available in the Simulink workspace. So if I go back to Simulink workspace, now we have some data available as scope data. So here is a scope data available in the workspace. It's an out data set, and here you can find out the scope data, and if you click on the scope data, here you will have 1 and 2 signals, and they are basically all the values available as data set, right? So if you click on the values, you will get all the values, and for my simulation I kept it 360 value constant, and that is what we are getting in the data. Now this is going to be the workspace, and from here you can actually copy your data and maybe paste it to an Excel sheet as a output result. So this is how you can use the Excel for taking the data in and out. In this session, we are going to learn about control logic and Stateflow. So it is very important in electromechanical system that we apply the control logic, and with the Simulink Stateflow features, we are going to implement this. So we'll learn what is basically a control logic and how this can be implemented in a Simulink environment using a new feature called Stateflow. So what is a control logic? Let me give you an example. An automatic washing machine is going to switch between different operating states. So you must be knowing how does an automatic washing machine works. In an automatic washing machine, you have to simply add your clothes and turn on the supply and select how you want to proceed. So maybe some initial configuration may be required from the user, but afterwards this will be considered as fully automatic. So let us understand what is the meaning of switches between different operating state. So by switches I mean that it is nothing but changing from one operating state to different operating state. What are the operating states? So let's understand what are the states of a washing machine which is fully automatic. So let's see, the first state is filling the water. So initially the washing machine drum is empty and you have added the clothes, and here the water is going to be filled up. So what is our initial condition? Let's say the supply is available and the clothes are also kept inside, right? And there will be some type of sensors which is going to check out what is the weight of the clothes, and accordingly the medium, high or low duty will be selected. So the first activity, or we can say state, is filling the water. Once the water is filled up and you have added enough of detergent or maybe the washing machine liquid, then the washing is going to get started. Washing is nothing but the washing machine motor is going to run in forward and reverse direction, and the clothes along with the water, they are going to get washed. So once the washing is done, a rinsing activity is going to get started. So rinsing is nothing but to get the water out, and that may involve draining of the water, and the clothes will get dried out. So how the other states are changed? What will happen after the rinsing? So maybe you need to wash your clothes at least in this loop by let's say 2 times. So this is going to be repeated 2 times, and once the rinsing is finished in the second round, the spinning is going to occur. Now the clothes are going to get dry. So for dryer or for drying out the clothes, the spinning is going to occur. And now this may require some hot air or maybe some kind of an heating. So this is the overall control logic of a washing machine. So initially these are all called the states or the operating modes. So if you see, at any point of time in your washing machine, once the supply is on and the clothes are added, till it is not going to get finished, let's say the last state is finish and the initial state is, let's say, the start. So before the start and after the end of finish, we are not going to discuss those situations. So we assume that the start is done and the water is going to get filled. So all these states are followed one after another, and the decisions are made according to what is the condition of washing. And what do you think are those conditions? Yes, washing machine operates on the conditions based on the time delays. So a washing machine, according to the duty, now this duty may be medium or high or low. Now that depends on amount of clothes you are adding. So based on the duty, this delay is selected, and according to this delay in each state. So whenever the state is being changed from filling of the water to the washing, there will be some kind of a delay which will allow the water to be filled to certain level. So once the washing has started, another timer is going to start, and it will, let's say, calculate the 10 minutes. So now once the 10 minute has been finished, the state is going to change after the 10-minute delay, and it will be in the rinsing state. And after the rinsing is done for, let's say, 5 minutes, the water will be filled again, and the count is going to increase from 1 to 2, and then the spinning and heating will occur for drying purpose. So this is how an automatic washing machine works. If you have observed, the logic behind the operation is divided into the time delays and the different states. So let us understand what is exactly the control logic by another example. So another example is your car gear system, right? So how do you drive a car which is having a manual transmission system? So initially you have started your car and you will be keeping in a gear, let's say, which is gear number 1, till the speed is above 15 kilometers per hour. And similarly you will keep in gear 2 till the speed is, let's say, 25 kilometers per hour, and you will upshift the gear and it will be, let's say, around 40 kilometers per hour. So these are let's say some of the standard guidelines in order to operate your car efficiently in a typical gear. Now what is the logic over here? So check the speed. What is the value of the speed now? And accordingly this gear positions are going to be chosen from either 1, 2, 3 or 4, 5 and 6. So all these gear positions will be selected based on the sensed value of the speed. And actually it's not just a number. Whatever I have written is just a high number, but it is actually going to be a range. So when your speed is going to fall from below 40, then you need to shift down to second gear, and if the speed falls again below 15, then you need to again shift down to the first gear. So shift up and shift down is called a logic, or they are the important decisions made by the driver. Now what are the standard driving conditions, right? And if you implement this in a kind of a flow chart, then it becomes your control logic for operating or shifting the gears. So shifting a gear is another example of a control logic where you start your car and let's say the engine is running. Now you have an input which is nothing but a speed over here. Now based on this value of the speed, here is a condition check block, and what is the value of the speed? So is the value of the speed between 10 and 15? Then you are going to follow the process 1 or let's say gear 1. If the value of the speed is above 15 and below 25, then probably you will be running your vehicle in the gear 2 by let's say process 2, and here you may have a different branches and you can decide on which gear you want to shift it to. So this flowchart can be actually continuous where you check the input continuously, right? So it's not going to be a one-time kind of a flowchart where it will start and then its input is detected and the process is done and that's an end. So it's not going to be end unless and until your engine is stopped. So this is another example of a control logic where you can implement your logic in terms of a flowchart or core logic. Now this logic may be in terms of your script, right? You may write a C program or a Matlab script in order to solve this logic. So all this script written is going to be a kind of a language which is a flowchart converted into a C language. Now we are going to learn a different language in the Simulink where this flowchart or the logic is converted into a state flow. So here we are going to learn about a new technique which is known as a state flow. So state flow is basically a new feature of converting your logic into a systematical arrangement. Let's understand what is a state flow. Before the state flow, we need to actually know what is the state machine. So state flow is a Matlab Simulink tool where you can implement the state machine. So what is a state? State is nothing but the operating mode of a system. Let's take an example of a car. So this car status or let's say the operating mode of a car can be either in the parking mode, the engine is off, or the engine is on and the vehicle is accelerating or maybe braking or it's running at a constant speed, or it is the engine is running and it is idle or it's not moving ahead maybe at a traffic junction, or you are taking it out from a parking and getting it reverse, or the state of a car may be fueling where it's idle as well as the fuel is added, or it can be another state of the idle category where it is getting repaired in a garage. So these are states of a system or let's say states of a car. Now state changes based on some decisions, right? So what are those important decisions? So whether you are going from parking to road, or whether there is a traffic or no traffic, and if there is no traffic, probably you may ride at a higher speed and accelerate your vehicle, or you may run at a constant speed. Or if the condition is fuel is going to be near to empty level, then you will go for fueling. So what are the decision making parameters? So decision making parameters may be the traffic, the fuel level, and many other road conditions. So inputs and conditions together are going to decide the state transition. So the state transition is very, very important where we move from let's say accelerating to braking. So accelerating to braking where the condition may be the traffic is equal to 1. So you have detected the traffic has now arisen, or let's say the situation is such that there is a traffic on the road, and instead of applying the accelerator you will release it and you will apply the brake. So this is one such situation of the state machine and state transition. So the state machine and the state transition can help us to make a chart in a Matlab Simulink state flow environment. So what is again a state machine? So let's discuss more about it. So here we are considering an event-driven system. So basically the state machine implements an event-driven system. So the event-driven system is nothing but the system which responds to an event by making the transition or the change from one state to another state. So here this transition is going to occur based on the condition, if the condition is going to be true, right? So you will be continuously checking the condition. So here is the logic where if the fuel is empty, right, you will continuously check the fuel level. If the fuel level is below, let's say 10% of the fuel full tank capacity, then this condition is going to be true and the driver is going to search for a gas station or a petrol station. This is called a transition decision making. So the Matlab state flow is such a graphical representation of finite state machine. Now instead of writing a script, maybe in C language or the Matlab script.m files, you can do this by making some charts like this. So here you have a block 1, here you have a block 2, and you can decide when the event or when the state is going to change from block 1 to 2, or when the state is going to change from block 2 to 3, or maybe again back to block 1. So the Matlab state flow is a graphical representation of your logic. So whatever is your flow chart or whatever is your logic, that can be implemented in a Matlab state flow environment. Now without discussing more about this, let's take up a untitled file and implement the state flow. So here I have a blank model and we want to actually make a very simple state flow arrangement where if the value of an input, then it is going to give us +1, and if the value of the input is less than 1, then it is going to give us the -1. The example which we are trying to take is based on the input value, right? So we are going to check the input value whether it is less than 0, which is negative, or if it is greater than 0, which is positive. And if such a case is there, then we are going to have the output equals to -1, and if the value is greater than 0, then we have the output equals to +1. So here this is going to be the condition check and this is going to be the output. So how do we implement this in a state machine? So this is going to be the input where the value is going to be continuously checked for this condition. So these are going to be the condition, and we are not going to worry about what if the value is exactly equal to 0, and that can be also implemented as well by adding another state where the output is equal to 0. If the value is equal to 0, the output is equal to 0, or the output is not defined. So we have three things: input, output, condition, and the different states which are high and low. So let us take a blank file. So let me show you how we can actually create a finite state machine in the Matlab. So here what you see is a chart, and this is how the chart will look like from a block point of view. Now once you double click on the chart, it is going to enter into a different domain, right? So whatever you see over here, all these things which are related to this and all this window and maybe other this stuff and this stuff, they are going to change once you enter into the chart mode, because the chart mode is different than the Simulink mode. So chart mode is where you actually create your control logic. Whatever you have observed, right? So earlier window was having the white background and now you have a light yellow background. Apart from that, you also have some symbols coming up over here. So how do we create a chart? To create a chart, first we need to define a state. So in our example, how do we define a state? So let's say there are two states and its name is high, where the value is greater than 0, and here is the state high, and let me take another state where it is low. So these are the two states, and we have named them as high and low. Probably you can name as positive and negative as well. So what we want in this states that we have to write here, and whatever you see, this arrow is going to be the entry point. So whatever the first state you enter in your chart, that will come with this entry point. And probably you can define an instruction over here, and you may choose to not define as well. What we want when the high state is going to be there. So let's say at the time of entry, and the entry is going to be the keyword, we create an output variable which is value, and we keep the value equals to 1 and a semicolon. So this is going to be a kind of a Matlab or a C kind of syntax, and you can add it or enter over here itself. Here I'm defining the entry point where the value is going to be -1. Now, when does the value change from high to low? And what is the error we are getting over here? So here we are getting something called unreachable state. What is the reason behind unreachable state? Because this is going to be there for this state, and which is a default entry point. Now there is no such entry point for this block, and therefore it is showing an error. So how do we define connection of this state and this state? So that can be defined by creating an arrow from this to this. How do you create an arrow? So once you click on the border of a state, here is the border of a state, and from there you will see the symbol has changed to a plus, and then or you can draw an arrow. Now that arrow should be pointing to some other state of your interest. So let's say my condition is the input is less than 0. So if the input is less than 0, the brackets will come automatically, and I just need to now click on the side, and my condition is set. So input less than 0, then the high state is going to get changed to the low. Similarly, we need to change it to the low state, changing into high if the input is greater than 0. So if input is greater than 0, then the low state will change it to high. Now, how do we check about the logic? Now, are we clear in syntax? Did we make any mistake? Now, in order to check this, what you have to do simply is click the run button. So when you click the run button, it is going to ask you about unresolved symbols. So here you see there are certain unresolved symbols which are placed in the chart. What are those unresolved symbols? Those unresolved symbols are nothing but input. The Matlab or the Simulink doesn't know what is an input or where have you declared it, and the other is the value. So let us declare input and value. So how do we declare whatever conditions we have taken? Please remember, we need not to declare the state. The high and the low are two different states, and we need not to declare them because they are not the variables or the symbols. They are just representing the name of a state. In order to declare the value and the input, what we have to do is we need to open up the symbols pane from this option. So here is a symbol pane, and from where you can get it, this is the place where you can get the symbols pane. So in the symbols area, we can actually declare the values and the input. So here comes the value, and it is declared as an undefined symbol. And what we can do is we can actually create it by choosing its type. So we can, what is the value? Value is the output data for us, and therefore out of this all options we are going to select the value as a output data. So this is the output data, and probably now there is no problem. So the now value is declared. We can also create another data, and we can name them as the input can be an input data. So now we have declared two symbols, value and the input over here, and after this what we need to do is let's come out of this chart and let's see how does the chart look from inside. So let me zoom in, and here is what you see. So you see actually a transparent diagram where what is inside a block represented as a chart. So now whatever is the value, I need to place it as a scope, right? I'm going to connect this as a scope. So let me connect this to the scope, and it's going to display what is the value. And let's connect some input. What kind of input we can connect here? So what is our logic? We can give any random number or any value which is becoming positive and negative. What kind of blocks are coming into your mind? What you will search over here? Maybe a sine wave. Okay, the sine wave will also go positive and negative. Or you can use a repeating sequence as well. So let me use a repeating sequence over here which will go positive and negative, and we want to actually analyze both together what is happening with input and output at the same time. So what we want is this value to get changed from 1 and -1 when the input values are greater than 0 and less than 0. So let me set this repeating sequence. So I'm going to set here the timing values which are, let's say, let me define the output values. I want this to go to, let's say, 0 to 20, then again 20 to 0, and then -20, and then again 0. So I have this 5 values at the equal instant of time, and those time instants are, let's say, 0 to 2 seconds, then 4, then 6 and 8. So this means the 0 at the 0 instant the value is 0, at second 2 the value is 20, at second 4 the value is again going to reach down to actually the 0, and you will have finally 0 at the end of 8 seconds. So look at the way which repeating sequence looks like. So this is exactly how the repeating sequence we are giving as input to this block. Now what is going to be the output? What we are expecting in the output? So here, this is our input. Let me draw the graph of the input over here, and this is going to be like this, a triangular wave. Maybe one time period is going to look like this. And what is going to be the output? So the value is positive for the entire half cycle. So here the value remains positive for all this duration. So in all this duration, which is from this to this, what we are going to get in the output is +1 constant value. So this is a +1, and this is going to be 0 and 20, again 0 over here and -20 over here. Now what will happen when the value goes negative? So the value is going to be -1 for this much duration of time. So this is going to be the output, right? Now probably if you have given a sine wave, then also the output will be similar, right? So what is our control logic? Basically is checking the value positive or negative. So if the value is positive, then answer is +1. If the value is negative, answer is -1. And this simple logic can be used in many engineering applications. Now let me go back to our untitled file and run this simulation for 20 seconds. Do we have any errors? Probably not. And our simulation is run, and this is what we are getting in the output. So whenever the blue is positive, which is let me show you the legend, the repeating sequence, whenever it's positive, the output is positive. Whenever it goes negative, the output is negative. So this is what we were expecting. And now if you actually wish to get what is happening step by step, then you can see the simulation as well. So you can click on step forward, and you can run your simulation in each step. So if I can write, so here comes the high value. In the next step, here is again the high value again, and based on my time step, the value is now getting decreased, right? So now my positive half cycle is coming to an end, and therefore we are going to observe in next few steps the state will change from the high to low. So here comes a 0, now comes the negative, and here what you have seen is the state has changed because this condition has become true, and earlier the high block was active with the blue line. Now the low state is active. So the low state is going to remain active until the value over here goes negative or remains negative, right? So if you click on this, then again now 0, and again the state will be changed. So this is how you can debug your diagram by using the step forward. Let's say we have a traffic light system where it's a crossroad like this. So there is one road going in this direction and another traffic coming in this direction. So this is one road, and similarly the junction is having another road at 90 degree where the traffic goes like this, and the traffic is going to come from top to bottom like this. Now at this junction we are going to have some signals. So here we have the signals, let's say for this passengers or travelers. Here we have another signal and another signal over here and another signal over here. So those riders who are coming over here at this place, they are going to observe this signal. Now the signals, for simplicity, assume only two states, red and green. Now once this is going to be red, all this traffic will be stopped here. Whenever the green signal goes on, the traffic will move. And let's assume for the simplicity there is no right or no left condition, and therefore there are only two possibilities where either this traffic and this traffic will move together on this road, or they will be stopped and this traffic will move forward in this road. So these are the two conditions, and therefore let's say a traffic signal or a traffic light system is implemented in such a way that this becomes green and this also becomes green over here, and this remains green for, let's say, 30 seconds. So 30 seconds this too remains green, and this audience, they will travel or they are going to move. Now after 30 seconds this will go red, and for another 30 seconds this too will remain green. So what is happening actually, at the interval of 30 seconds, this green lights are actually changing the state. So here comes the state logic, and here comes a delay of 30 seconds. Now how do we apply the delay in the state flow diagram or a chart? So let me show you the traffic light system in the state flow arrangement. So what you see over here is the north, east, south and west, and there are some indicators. So these are actually the lamp, and which is part of the Simulink library of a dashboard category. So if you go to the Simulink library browser, and if you see over here you will be able to find the dashboard systems and the indicators. So it's actually over here, the dashboard. So when you click on the dashboard, what kind of system you will see? So you will see a kind of graphical user interface. So here comes a lamp, here you have a slider switch for turning it on and off, and here you have probably a gauge. It may indicate the speed of a vehicle, for example, or you have a plot, or a number display like this. So these are the dashboard elements which may be very useful when it comes to a graphical user interface in the Matlab environment. So these are all such lamps, and if I double click on this is a lamp connected to the north signal. And how do we run this simulation? So I'm going to run this simulation for 150 seconds and let's observe what is happening. So I click on the run, and now let me show you all lights. So here you have north and south becoming green together and west and east becoming green together. So while the other things are green, the other side is going to be in stop mode, or they will be red. So red indicates the stop state, the green indicates the go state. So the stop and go are provided with a delay. So let's understand how does this chart is built. So I'm going to stop my simulation over here, and I hope you are able to understand what kind of a situation we have created. So I'm stopping my simulation over here. Let me go into this chart and understand how it works. So here U is going to be our default input, and there are north, east, south and west 4 different states. So Y, Z, R and X are actually those variables which represents dashboard lights. Now what is that condition we are checking in? Are we observing the traffic? No, probably our traffic light system is delay driven, so it's fixed after every 20 seconds. In the previous example I told you about 30 seconds, but we can consider any different second. So after 20 seconds is the condition which we have given over here. So no matter whether this state is going to be true or false, after 20 seconds it is going to come to this state, and after 40 seconds it will come to the next state, and after another 20 seconds it will come to this state where we are changing all those values of red and green lights. So probably we have 8 number of red and green lights and different states. So instead of changing its color of a same lamp, which is a case of a reality in real situation, probably you also have different lights, right? So in a traffic junction you have a different lights for green and a red. So we have total 8 number of lights and they are operated together. So this is how it is implemented. So the only new thing over here in this state flow is the delay. So now this delay is going to be according to the starting. So after 20 second is going to be the case when the simulation has started. So after 40 second, which means that the 20 second different from the N2 state. Now what will happen once the all traffic from north to south and east to west has been finished? So now you have to repeat it. So this repeat is through this condition. And what is this point? Because it was difficult to connect this arrow to the very first state, which is N1, we have created a junction, and you can find out a junction over here. So this is a junction where you can actually change, or you can use a routing of a signal which represents a condition. Because we haven't provided any condition over here, it is going to follow the same condition which is after 160 seconds. So this is how a traffic light system works. Now you have got enough idea about how the state flow works. Thank you.